Okay, all right. So now we are going to discuss the numericals related to buck converter and boost converter. Okay, so let us first discuss this. A buck converter is operating at 2 kilohertz from 100 volt DC source. Okay, it has L by R ratio of 6 millisecond and a load resistance of 10 ohm. Find the mean load current and magnitude of ripple current for a load voltage of 50 volt. Also calculate the maximum and minimum values of inductor current, right? So this numerical is related to the buck converter. Let us first note the given data. Yes. So we are having a switching frequency is a 2 kilohertz, which is equal to 2 into 10 to the power 3 hertz, right? 100 volt DC source. So input voltage Vs is equal to 100 volt. It has a L by R ratio 6 into 10 to the power minus 3 second. Okay, so it is like a time constant they have given. And the load resistance of 10 ohm, R is equal to 10 ohm. R we know, L by R we know. So from this we can find L, right? Find the mean load current, that is I0 average. We need to find. Next, find the and magnitude of ripple current for load voltage of 50 volt. V0 is given. V0 is equal to 50 volt. Magnitude of ripple current, that is a delta IL. We need to find. Also calculate the maximum and minimum values of inductor current. Okay, so next we need to find it IL mean and IL max. Okay, that is in our case we consider it as I1 and I2, right? So it is a buck converter. So buck converter, first of all, recall the circuit diagram. In the buck converter, we're having a supply voltage, right? Next, a switch, diode, and inductor. Inductor is connected at the load side. In a buck converter, inductor is connected at the load side. Whereas if you check the boost converter, inductor is connected at the supply side. Okay, in the boost converter, it is right. So now, yes, we're having a L by R ratio and R. So from this, can we find L? Yes, we can write. Yes, let me write it as, therefore L is equal to, it is a 6 milli into R na, 6 into 10 to the power minus 3 into R. R is a 10. So it is equal to 60 into 10 to the power minus 3 Henry. Okay. So this is a L. Next, R is given, V0 is given. So can we find the first I0 average? Yes, I0 average is equal to V0 average by R. Okay. So we can write I0 average is equal to V0 average divided by R. So it is equal to V0 average 50 volt and R is 10 ohm. So it is a 50 by 10. So it is equal to 5 ampere. Now if you recall in the buck converter, average value of inductor current and average value of load current, both are same or different? Both are same. Yes or no? Right? So I can write it as a IL average is equal to I0 average is equal to 5 ampere. So we're having a IL average is 5 ampere. Now next, in order to find the delta IL, because in order to find the IL mean and IL max, we require delta IL na. IL max means what? It is IL average plus delta IL by 2, and IL mean is it is IL average minus delta IL by 2. Okay, so we need to find the delta IL first, right? How to find the delta IL? For delta IL, if you recall the circuit, during we are having the expression for delta IL also. Okay, but whether in a final examination it is easy to recall the circuit diagram or it is easy to recall the expression? Yes, definitely it will be easy to recall the circuit diagram, right? So how the circuit diagram we are having for the buck converter? If you check, during t is equal to 0 to t on, during t is equal to 0 to t on, that is dt. T on means dt na. So we're having the circuit diagram. It is like this. It is a switch here. This switch is connected. That is a on state, right? Inductor. Here it is a capacitor, and here it is a load. Yes or no? Yes, here we are having a diode, but that diode is a open circuit during the on state. So this voltage is like a Vs. This is VL, L, IL, capacitor C, and this is V0, right? I0. And in order to find the delta IL, yes, we applied the KVL to the outer loop, na? Right? So same thing, let me do. Yes, KVL to outer loop. KVL to outer loop. So from that I can write Vs minus VL minus V0 is equal to 0. So therefore VL is equal to Vs minus V0. What is VL? VL is L into DIL by dt. So it is a L into DIL by dt is equal to Vs minus V0. No? Right? Now how the current is changing during on time? It is changing from I1 to I2 now. Right? So I can write it as a L into DIL by dt means it is a IL max, or you can write I2, okay, minus IL min divided by dt. That is a change in the time. Change in the time is a T on is equal to Vs minus V0. Recall the same circuit operation, whatever we discussed in the yesterday's session. Okay. So further I can write it as a IL max minus IL means IL min is nothing but delta IL, which is equal to Vs minus V0, right, into T on. T on means dt, right, divided by L. Is this clear? Vs minus V0 into T on means dt divided by L. So same delta IL. Now Vs we know, you can check Vs. It is 100 volt and V0 is a 50 volt. Okay, so I can write it as a 100 minus 50 into duty cycle. Yes, they have not given the duty cycle directly, but we can find. Okay, output voltage is a 50 volt, input voltage is a 100 volt. So duty cycle is equal to 50 by 100, na? Right? So I can write it as a 50 by 100. This is a duty cycle, right? Into time t. Instead of time, I will write it as a frequency, right? So divided by L. L is a 60 into 10 to the power minus 3 into t. This t, I am writing it as a, in terms of frequency, right? 1 by t means the frequency. So if I write here frequency, if you check the frequency is 2 kilohertz. So 2 into 10 to the power 3. So from this we can get, it is, yes, 50 into 0.5 divided by 60 into 2, right? 0.208, 0.208 ampere. This is the delta IL we are having. Is this clear? Either you can directly put in an expression, because the same expression we got, right? Next, either you can memorize this expression, or you can simply simplify in this way, right? Next, so this is the delta IL. How to find the IL mean and IL max? IL max is equal to IL average plus delta IL by 2. Okay, delta IL by 2. Okay, so it is equal to IL average. We have written it is 5 ampere. So it is a 5 plus 0.208 divided by 2. So if you check, it is equal to 5.104 ampere. This is a IL max, right? Similarly, we can find IL min. IL min is equal to IL average minus delta IL divided by 2. So which is equal to 5 minus 0.208 divided by 2. So if you check, it is equal to 4.896. Okay, 4.896 ampere. Is this clear? Right? Yes. Okay. So this is about the numerical number 1, right? Please check. We have calculated IL mean, IL max, delta IL, okay, and I0 average, right? Simple example. The thing is, you need to recall the buck converter. Actually, you need to recall the buck converter circuit diagram. Next, let us discuss the next example. Yes. In the circuit shown, an ideal switch ES is operated at 100 kilohertz. Switching frequency is 100K with a duty ratio of 50%. D. given that delta IC, they have given a delta IC now is a 1.6 ampere peak to peak, and I0 is the 5 ampere DC. I0 is a constant 5 ampere. The peak current in S is, right? So source peak current in a switch they have asked. Okay, next second bit, also find the average switch current and inductance value. Okay, so let me first note the given data. Switching frequency is given, it is 100 kilohertz. 100 into 10 to the power 3 hertz. This is switching frequency. Duty cycle D is equal to 0.5, 50%, that is a 0.5. Given that delta IC is equal to 1.6 ampere. Peak to peak, okay, that is a, yes, delta IC peak to peak. I0 is a 5 ampere. I0 is a constant, that is a 5 ampere. Our task is to find the peak current in S, that is a IS peak. We need to find, at the same time also find average switch current, that is a ISW average, and inductance value, and L value also we need to find. Okay, so L value is required, ISW average and IS peak. Okay, we need to find. So here if you check, yes, whether it is a buck or boost converter, it is a buck converter only. Yes or no? This is a buck converter, right? Now I0 they have given, it is a 5 ampere. Our task is to find the IS peak. Now my question is whether the IS peak and IL peak both will be same or different. Whether IS peak and IL peak both will be same or different. IL peak is nothing but the peak value of current flowing through the inductor. IS peak is nothing but the current flowing through the switch. Okay, peak value of the switch current. You can check the circuit operation when switch is closed. When switch is closed, yes, when switch is closed, current will flow like this, na? Diode will be open circuit. So inductor, it is like inductor storing the energy. So you can recall the yesterday we drawn the waveform of switch current. Switch current waveform during 0 to t on, it is same as that of your inductor current, na? Right? So peak value of switch current is nothing but peak value of inductor current only, right? So how to find the inductor current peak value? We know it is a IL average plus delta IL by 2, na? So IL average is equal to I0, it is a buck converter. IL average and I0 average both are same, na? Right? So I0 average is equal to 5 ampere. So therefore your IL average will be equal to 5 ampere only. The only thing is we need to find the, yes, delta IL. We need to find the delta IL, right? So let me write first. IL average is equal to I0 average is equal to I0, which is equal to, it is a 5 ampere. It is equal to 5 ampere value, right? So this is the average load current. Okay, this is the average load current and average inductor current. Next, they have given the delta IC. Delta IC is 1.6 ampere. So if you recall the IC waveform, yesterday we drawn the IC waveform for buck converter. Yes, it is like from 0 to t on to t. How is the waveform? It is like this. Same waveform we discussed in the yesterday's session. Right? So what was this magnitude? This magnitude was minus delta IL by 2. And here it is a plus delta IL by 2, na? Yes or no? So what is the delta IC? Delta IC is nothing but this difference between peak to peak, means delta IL by 2 minus of minus delta IL by 2. That is nothing but your delta IC. This is the delta IC. Are you getting the point? So from this, can I say that delta IC means delta IL by 2 minus of minus delta IL by 2. Okay, so let me write delta IC is equal to delta IL by 2 minus of minus delta IL by 2. So it is like delta IL by 2 plus delta IL by 2, which is equal to delta IL only. Is this clear? So delta IC means indirectly they have given the delta IL value. So what is delta IC? It is equal to 1.6. So can I write delta IL is also equal to 1.6 ampere? Is this clear? Right? Same expression, this waveform of IC, yesterday's session we already discussed, right? For buck converter, please check. So this is delta IC, delta IL is 1.6. Now, what is the IS peak? So now IS peak is equal to IL peak, na? Which is equal to IL average plus delta IL by 2, na? right? So this can be written as IL average. We know it is a 5 ampere. So it is a 5 plus 1.6 by 2. So it is equal to 5.8 ampere, right? This is the IS peak. Peak value of switch current. Peak value of switch current, right? So IS peak is 5.8. So you can check the option. It is a 5.8. Also find the average switch current and inductance value. Okay, so how to find the average value of the switch current? Average value of the switch current, right? So please check. Yesterday we already written the switch current average value expression, or in another way we can find it like this also. Switch current, suppose ISW or IS, you can say this is time t, 0 to t on, switch is in a on state, t on to t, switch is in a off state now. So current flow through the switch, it is like a same as that of the inductor current, right? So you can check, this is increasing from this value, okay, and after that it will be like this. Yes or no, right? So this peak value we know, right? This peak value we know. Just now we calculated this value is 5.8 ampere. This is a 5.8 ampere. Are you getting the point, right? So we calculated this value is equal to 5.8 ampere. Now we need to find the IS average. So what we did, we approximated this IS waveform na in the yesterday session, okay, with the IL average for this portion. So it is like this. T on T, we approximated like this. This is like your IL average. Okay, and this is a 0. Same. So now from this, what is IS average? IS average is equal to duty cycle D into IL average na. So you can check, it is duty cycle. It is a 0.5 into what is IL average? It is a 5 na. It is a 5 ampere. So 0. Into 5. So it is a 2.5 ampere. This is your IS average, right? IS average is 2.5 ampere. Okay. The next thing they asked is, that is ISW average, means switch current average value. Okay. Next, inductance value. Yes, they have asked for the inductance value. So how to find the inductance value? Here inductance value, it doesn't mean that it is a L critical. Please be careful. Inductance value means they have asked the value of inductor for whatever the circuit they have given here. Okay. So how to find the inductance value? Let us understand. So during T on, if you check, during T is equal to 0 to T on. Yes, how is the circuit? It is like a switch is closed and circuit will be like this. Na? Current is flowing from supply, switch, inductor and a load like this. Apply KVL to the loop. So I can say that it is plus Vs minus VL minus V0 is equal to 0. Okay. So it is plus Vs, that is plus 24 minus VL minus V0 na, minus V0 is equal to 0. So therefore VL is equal to 24 minus V0. What is the V0? We have written here. Yes. D is given 0.5. Supply voltage is 24. So we can find the V0, right? We can find the V0. So let me write it as 24 minus duty cycle D into supply voltage. So it is 24 minus 0.5 into 24. So it is equal to 12 volt. Na? This is a VL. So VL is equal to 12 volt. But during 0 to T on, how the inductor current is changing? Inductor current is changing from Imin to Imax, na? Right? So I can write VL with, I can replace VL as L DIL by dt is equal to 12 ampere. Right? So therefore, L into DIL is nothing but your delta IL. Check the IL waveform. You will understand during 0 to T on, inductor current is changing from I1 to I2. That is, the DIL is nothing but I2 minus I1. That is nothing but delta IL. Divided by dt. Dt is nothing but T on, which is equal to 12. Okay. So therefore, delta IL is equal to 12 into T on. Na? T on is nothing but dt only. That is D into T divided by L. Okay. So our task is to find the L actually. Okay. So instead of this, let me write it as L is equal to Yes, therefore L is equal to divided by delta IL, right? So this can be written as 12 into duty cycle is 0.5. I can write this T in terms of frequency. Delta IL we have written, it is a 1.6 into, check the frequency, it is 100K na? So it is 100 into 10 to the power 3. So please check L value. Yes, L is equal to 37.5. 375 or 37.5? 37.5 micro Henry or Farad? 37.5 micro Henry, right? So, is this clear? Okay, so 37.5 micro Henry, right? So this is about the second numerical, right? L value we have calculated. After that, they asked for the average value and the peak value. Okay. Next, let us discuss the third example. A buck converter has an input voltage VDC is equal to 15 volt. The required average output voltage V0 is equal to 5 volt. And the peak to peak output ripple voltage is a 10 millivolt. Okay, peak to peak. Delta V0 they have given. Delta V0 means delta VC. Okay. The switching frequency is 20 kilohertz. F is given. The peak to peak ripple current of inductor is limited to 0.5 ampere. Okay. Determine the duty cycle, right? Second bit filter inductance, third bit filter capacitance, and fourth bit critical inductance and critical capacitance for a resistance of 500 ohm. Okay. So let us first note the data. Yes. So here if you check, they have given VDC, that is a supply voltage, is equal to 15 volt and output voltage is equal to 5 volt. The peak to peak output ripple voltage, that is a delta V0, which is equal to delta VC, is equal to 10 into 10 to the power minus 3 volt. Okay. The switching frequency F is equal to 20K, 20 into 10 to the power 3 hertz. The peak to peak ripple current of inductor, that is a delta IL, is equal to 0.5 ampere. Determine the duty cycle. Okay, so first bit is, our task is to find the duty cycle. So let us find first the duty cycle. How to find duty cycle? This is the buck converter, right? In the buck converter, we know V0 is equal to D into Vs. Okay, so V0 is equal to duty cycle D into Vs means VDC in this case. So therefore D is equal to V0 upon VDC. So you can check 5 divided by 15. Na? So it is a 5 by 15. So it is a 1 by 3, which is equal to 0.333. Okay. This is the duty cycle D. Right. Second bit, they asked the filter inductance L value. Second bit L value. How to find the L value? Delta IL is given. They have asked the L value. Okay, so simply either during 0 to T on apply KVL to the loop, or during T on to T apply KVL to the loop. Okay, so during T is equal to 0 to T on. If you recall in the circuit of the buck converter, yes, we know equation is like plus V KVL equation, Vs plus Vs minus VL minus V0 na, plus Vs minus V0 minus VL is equal to 0. So therefore VL is equal to Vs minus V0. What is VL? VL is L into DIL by dt is equal to Vs minus V0. Okay. So now from this we can write it as, right here. Yes. Therefore our task is to find the L na. So L is equal to Vs minus V0 into dt is nothing but T on na, divided by DIL is nothing but delta IL. During 0 to T on, please check the waveform of IL, how it will be. Inductor will be storing the energy, na? Right? So you can check here, Vs is, they have given, it is a 15 minus V0 is 5 into T on is dt, na? divided by delta IL. Let me write delta IL value. It is a 0.5. So it is equal to 10 into duty cycle is just now we calculated 0.333. I am writing this T in terms of frequency. So it is a 0.5 into frequency is given 20K. Okay. So 20 into 10 to the power 3. Yes. Please check what is the value of L. .33 millihenry, right? 0.33 millihenry, correct? So 0.33 millihenry. This is the value of L. This is not L critical, be careful, right? This is the value of L in the circuit. .33 millihenry or 33.33 microhenry. Okay, anything you can write. Yes. Sir, why frequency term is denominator? Because you can check here in the numerator we have got time t na, and we know frequency is equal to 1 by t. Yes or no? So can I replace this t like a 1 by f? So that's why here I have replaced this t with like a 1 by f. Are you getting the point? Okay. So yes. Next they have asked the filter capacitance C. Okay, filter capacitance C value. Okay. So how to find the C value? They have given the delta V0, na? Right? Delta V0 they have given. You can check. Delta V0, which is equal to delta Vc, which is equal to, we know it is a delta Q by C, na? Delta Q by C. Yes or no? Right? And delta Vc or delta V0 they have given. How to find the delta Q? If you recall the circuit operation, whatever we discussed in the yesterday's session, delta Q means it is like a area under the triangle, na? Check the IC waveform. Check the IC waveform. In that we have represented the area under the triangle is a delta Q, na? What was that area? It is like 1 by 2 into delta IL by 2. Okay, into T by 2. 1 by 2 into delta IL by 2 into T by 2. Yes or no? Divided by C is equal to your delta Vc. Right? So now you can check delta IL, we know. T is nothing but a 1 by frequency, we know. And only thing is we need to find the C. Delta Vc is we know, right? So what is delta Vc? It is a 10 into 10 to the power minus 3. So let me write 10 into 10 to the power minus 3 is equal to, this is like a delta IL into, I'm representing this in terms of frequency, divided by 8 into Fc. Yes or no? Delta IL divided by 2, that will be 8 here, right? And T I have represented with the F, 1 by F, and C as it is. So is equal to delta IL, we know it is a 0.5 divided by 8 into frequency, it's a 20K, na? Into C. So what is the value of capacitor? Therefore C is equal to, please check what is the value of capacitor. Right? Either you can memorize the expression of delta Vc, whatever the expression we derived in the yesterday's session, or you can, yes, recall this expression, delta Vc is equal to delta Q by C. Okay. So yes, so from this C is equal to 312.5 microfarad, na? Please check once. 3.125 or 312.5? 312.5 microfarad, right? 312.5 microfarad. Is this clear? Right? Yes. 312.5 microfarad, right? So next they have asked for critical inductor and critical capacitor. Okay. So how to find the critical inductor value? Critical inductor means what? It is the value of inductor corresponding to the IL is a just continuous. Yes or no? IL is a just continuous. So we know, yes, when L is equal to L critical, when L is equal to L critical, it is like a conduction is a just continuous na. So IL is a just continuous. Just continuous. What is just continuous? We have discussed the same thing, right? Already. So corresponding to the just continuous, we know IL average is equal to what? It is a delta IL by 2 na? Because for the just continuous, recall the waveform of IL at t is equal to 0, it is 0. 0 to t on, it is starting from 0, it reaches the peak value na, right? And after that, during t off, okay, it will decrease, and at capital T, it will reach to the 0 again. Okay. So the delta IL is nothing but like a maximum value minus 0 value, because in this case, the minimum value is 0 na, right? So IL average is equal to delta IL by 2, right? Now, what is the IL average, right? So IL average we can represent as, yes, so IL average is nothing but your I0, which is equal to delta IL. So delta IL, can we write it as, because we know na, delta IL is equal to Vs minus V0. I am same recalling from that KVL expression na, only KVL expression, from that I am recalling it. Okay. So Vs minus V0 into dt na, right, divided by L. This is your delta IL. You can check VL is equal to L DIL by dt. So L into DIL divided by dt is equal to Vs minus V0. Okay. So same thing I am writing here. Vs minus V0 into dt divided by L. Okay, these two as it is. Now you can check Vs, we know, put here, it is a 15 minus V0 is 5 into D is 0.33 divided by 2 into, replace L with L critical. Okay, L critical, and into frequency, that is 20 into 10 to the power 3. This is I0. What is I0? Yes, for resistance of 500 ohm na, so we can write it as a I0 is equal to V0 divided by R, right? Okay, so from this we need to find the L critical. So therefore V0 by R, V0 whether we have calculated or not, yes, they have given, I think, right? So it is a 5 volt. So it is a 5 divided by 500 is equal to same thing, 10 into 0.333 divided by 2 into L critical into 20 into 10 to the power 3. So please check and find the value of L critical. Find the value of L critical. Yes, I think it is 8.33 millihenry na? Yes or no? Yes, 8.33 millihenry. Next, we need to find the C critical. Yes. For the C critical, if you recall, we have derived the expression 1 minus D upon 16 into Fs square into L na, right? So here we need to put L is nothing but your L critical. Okay, L is nothing but the L critical here, right? Because for this bit they have given the resistance value of 500 ohm. Okay, so for finding the L and C, we need to consider this resistance is 500 ohm. Okay, so it is, yes, let me write as LCR. So 1 minus 0.333 divided by 16 into frequency is a 20 into 10 to the power 3 square into, this is 8.33 into 10 to the power minus 6. Yes. So what is C critical? It is a 12.5 nanofarad. 12.5 nanofarad, right? Okay. Yes. Next example. Yes. The semiconductor switch shown in the figure is operated at a frequency of 20 kilohertz. Frequency is given 20K and a duty ratio of 0.5. D is equal to 0.5. The circuit operates in a steady state. Okay. Now you can check the steady state means what? Yes, it is like a current is increasing from same amount and again decreases and again increases, again decreases like thing. Okay. Next, so if you check this circuit is like your boost converter only. Let me redraw this circuit so that you will understand it is a boost converter only. Okay, so let me redraw it. This side we are having a V1 and here we are having a V2. Right? This is a 100 microhenry. This is a switch, yes. Okay. You can check this circuit and this circuit, both are the same. Okay. So the circuit is a boost converter. Inductor is connected at the source side. Inductor is connected at the source side. Okay. So it is a boost converter only. It is a boost converter. Here they have indicated input voltage is V1. Output voltage is V2. V1 and V2. Okay. Next. So let us note the given data. Frequency is 20K. 20 into 10 to the power 3 hertz. Duty cycle D is equal to 0.5. The circuit operates in steady state. First bit, the power transferred from DC voltage source V1 is 100 volt to a DC voltage source V2 is equal to 300 volt. Okay. So for the first bit, they have given V1 is equal to 100 volt, V2 is equal to 300 volt. And our task is to find the power transferred. Okay. So power transferred meaning either you can find the output power or you can find the input power. Okay. Because in the circuit, if you check, we're having inductor, diode, and a switch. Apart from the input and output side, we're having only inductor, diode, and a switch. Okay. So that's why the power consumed by these three elements will be 0. So whatever the supply power is always equal to your load power. Okay. So here V2 is 300 volt and our task is to find the power transferred. Power transferred. Yes, this is for the first bit. Okay. So let us first find duty cycle is 0.5. They have given input voltage is given V1 100 volt, V2 given 300 volt. So let us first check whether it is a continuous conduction or discontinuous conduction. Because if you recall, for the boost converter, what is the expression we are having? V0 is equal to 1 upon 1 minus D into Vs, na? Yes or no? Right? So let us check for the given duty cycle. Right? For the given duty cycle and for this given input voltage, whether we'll be getting output voltage as a 300 volt or not. Okay, let us discuss that first. So please check this. This is very important. Yes, first bit we are solving. For D is equal to 0.5 and V1 is equal to 100 volt. 100 volt. Okay, we know for boost converter. For boost converter, for continuous conduction, we know V0 is equal to 1 upon 1 minus D into Vs. Na? In this case, V0 means V2 and Vs is nothing but your input voltage. That is a V1 they have represented. So I can write it as a, or let me write it as which is equal to Vs. Okay. So it is 1 upon 1 minus 0.5 into Vs is nothing but 100. So you can check it is like 100 by 0.5. 100 by 0.5 means it is a 200 volt. So please try to understand what is the meaning of this. If your duty cycle is 0.5 and if the conduction is continuous, then the output voltage is equal to 200 volt. But as per the given data, the output voltage is a 300 volt they have mentioned. Okay. So can I say that as this output voltage is not equal to, yes, as V0 is not equal to V2, which is equal to 300 volt. Okay. So can I say that this is not a continuous conduction? The meaning is it is a discontinuous conduction. Are you getting the point? Okay. So it indicates conduction is a discontinuous. So therefore, discontinuous conduction, right? Please try to understand this thing. Okay, this is very important, because as and when they give the input voltage, output voltage and duty cycle directly, please first of all cross check it whether for the given duty cycle and the given input voltage, right, for the given converter, whether the output voltage whatever they have mentioned, will it match or not. Okay, so first of all we need to check whether it is a conduction is continuous or discontinuous. We have checked for by using the continuous conduction expression we have checked. Okay, and for D is equal to 0.5 and supply voltage is 100 volt, we got it is a 200 volt. The meaning is it is not equal to your whatever the given voltage. Okay, given voltage, output voltage they have given na, V2 is 300 volt they have given. Okay, and whatever we are getting with the duty cycle of 0.5, it is a 200 volt only, right? Means 200 volt is not equal to 300 volt. Okay, so that's why here the conduction is discontinuous conduction. Means output voltage whatever they have mentioned is greater than that of whatever the output voltage we are having with a continuous conduction. We know na, in the yesterday session we discussed discontinuous conduction mode output voltage is greater than continuous conduction mode output voltage. Okay, so this is greater na compared to that of this one. So that's why it is a discontinuous conduction, right? Discontinuous conduction. Now in the discontinuous conduction, what is the expression of V0? We derived V0 is equal to beta upon beta minus D na into Vs. Yes or no? Or in terms of V1, V2, let me write. So therefore V2 is equal to beta upon beta minus duty cycle is 0.5 into Vs is nothing but V1. Vs is nothing but V1. So what is V2? 300 volt, which is equal to beta. Beta we need to find, divided by beta minus 0.5 into V1. What is the V1? It is 100 volt na. So from this, can we find the beta? Yes, please check what is the beta. Please check the beta value. Yes, beta value. Can we write 300 divided by 100 means 3 na? So therefore 3 is equal to beta upon beta minus 0.5. So from this we can write it as a 3 beta minus 1.5 is equal to beta. So therefore if you check, beta is equal to, I think it is a 0.75 na? Yes, 0.75 right, 0.75. So this is the beta they have given. Yes or no, right? So 0.75, right? Okay, so are you getting the point? Means the conduction is not a continuous conduction, right? So here first of all we need to cross check whether it is a continuous or discontinuous conduction. From that we calculated that the conduction is a discontinuous, and if the conduction is discontinuous, then we have used the expression of the output voltage for the discontinuous conduction. From that we have calculated the beta now. So beta is equal to 0.75. Now let us discuss what we need to find. We are supposed to find the power transferred from source to the load. Power transferred from source to the load. What is the power transferred from source to the load? It is equal to either your source power or which is equal to either your load power. Okay. So suppose if I want to find the source power, source voltage they have given, it is a V1 which is equal to 100 volt. The only thing I need to find is a source current na, that is the IS we need to find. You can check, this is the IS. Yes or no? This IS we need to find. Okay. Now how will the waveform of IS? How will the waveform of IS? When switch is in a on state, inductor go on storing the energy. IS and IL both are same or different? Both are same. When switch is in an off state, inductor releases the energy. IS and IL both will be same or different? Both will be same only. Yes or no? Right? So here IS average is nothing but your IL average. IS average is nothing but the IL average, right? So let me draw the waveform of IS first. Okay, so IS waveform, which is same as that of the IL waveform. T1 means dt. This is a beta T, and this is a T we are having. Okay, so waveform is like this. Inductor stores energy, discontinuous conduction. So definitely it should start from 0 only, right? From dt to beta T, it decreases. It should be linear, right? Decreases, and after that it is a 0, and again the same repeats. Okay, so this is like your IS peak, or let me write it as IL max. This is like your IL max. Yes or no, right? This is 0. Now if you check here, okay, so this is like a triangle. So if I want to find the IS average value, I need to find the area under the triangle. In order to find the area under the triangle, right, I need to find the IL max, because we know beta T already. We have calculated the beta value now, right? So only thing is we need to find the IL max. So how to find the IL max? For finding the IL max, either during when the switch is in an on state, we can apply KVL, and we can write plus V1 minus VL is equal to 0. But the thing is, suppose if you write like that, okay, so when during T is equal to 0 to T on, during T is equal to 0 to T on, yes, switch is on state, means your VL is equal to VS. VL is L into DIL by dt is equal to VS. Okay, so therefore I can write it as a L into DIL is nothing but, you can check how the current is changing, 0 to the IL max. That is nothing but the delta IL, na? That is changes like your IL max only. Are you getting the point? How the current is changing? IL max minus 0. So that is IL max only. Divided by dt, that is a on time, na? So dt, which is equal to VS. So now in this, if I want to find the IL max, it is equal to VS into dt divided by L, na? Then yes, first thing is we need to know the T. But if you check the circuit given data, they have not given the switching frequency. Yes or no? You can check the switching frequency they have given. Yes. Then it is good. Switching frequency is 20 kilohertz. I'm sorry. Switching frequency is 20 kilohertz. So I can directly write it is a 20K, na? Duty cycle is equal to 0.5. So we can find here directly. Yes. So therefore IL max, let me write IL max is equal to VS, that is 100 into 0.5. I'm writing this T in terms of frequency divided by inductor L into frequency. So it is equal to 100 into 0.5 divided by L value. Yes, it is 100 microhenry. 100 into 10 to the power minus 6 into frequency. It is a 20K. 20 into 10 to the power 3. So if you check IL max, yes, please simplify it. Yes, it is a 25, right? 25 ampere. IL max is a 25 ampere. IL max is 25. Now, knowing the IL max, can we find the IS average? Yes, we can find the IS average. How to find the IS average? You can check 0 to beta T only we are having a triangle. Okay. So can I say that IS average is area under the triangle divided by the total time T, right? So let me write IS average. So now IS average is equal to 1 by 2, that is the area of the triangle, na? So 1 by 2 into IL max into beta T divided by total time T. Okay, so you can check T will get cancelled out. So it is a 1/2 into 25 into beta, it is a 0.75. Yes, it is a 1/2 into 25 into 0.75. So if you simplify it, we will be getting 9.375, right? Yes. If switching frequency is not given, we will discuss. Okay, Manikumar. So, because in one of the example, the same thing is there, right? So 9.375. So it is a 9.375 ampere. That is the IS average. Is this clear? So what is the power transferred? Therefore, power transferred from source to load is equal to Vs into Is average. So it is equal to Vs is nothing but V1 into Is average, which is equal to 100 into 9.375. So it is equal to 937.5 watts, right? 937.5 watts. Okay. So this is for the first bit, right? Answer for the first bit. Yes. What about the second bit? Please read the second bit. I am expecting the answer from you guys for second bit. Same thing in case of V2 is 250 volt. Then find the power transferred from DC voltage source V1 to V2. Yes, come on. If V2 is given, it is a 250 volt, right? Then what we yes in the whatever the procedure we followed, the same procedure we need to yes same steps we need to follow again. We need to find the beta first, or let us first check whether the conduction is a continuous or discontinuous. Whether the conduction is a continuous or discontinuous. Imtiaz, how it is a continuous?
It is discontinuous, sir.
Yes, it is a discontinuous only. Yes or no? Right? So conduction is discontinuous. So which expression of V0 we need to write? We need to write V0 is beta upon beta minus D into Vs. D is given, it is 0.5. So first find the beta value. Now here instead of this 300, here it will be 250 na? So it is like 250 upon beta minus beta minus 0.5 into 100. Yes or no? Please try to simplify this and find the value of beta first. Yes, 0.8333, right? 0.833. The beta value is. Yes or no? So if beta is 0.833, yes, if beta is 0.833, now what will the IL max? What will be the IL max? Don't tell me the final answer from the booklet. Okay. Try to simplify it. Right? Okay, solved. Then good. Okay. IL max will be same or it will be different? Because during 0 to T on VL is equal to Vs we are having na? Yes or no? D is as it is. T is also no change. So IL max will be your same 25 ampere. It will remain as it is. Yes or no? Right. Now what about the? Yes, only the area under the triangle will change. Correct. Okay. 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 Right. So what is the final answer? Yes. What is the IS average? Please check once. It is 1/2 into 25 into 0.8333 na? Okay. So IS average is 10.4125, right? 10.4125. Okay. And the power is 1041.25, right? 1041.25. Is this clear? Right? So the second bit, those who are not solved, the second bit is the homework for you. Okay. So second bit, it is a homework. Same steps we need to follow. Next. Yes. Let us discuss the next example. In the figure shown below, the chopper feeds a resistive load from a battery source. MOSFET Q is switched at 250 kilohertz with a duty ratio of 0.4. All elements of the circuit are assumed to be ideal. The average source current in steady state is, okay. And the second bit, the peak to peak source current ripple, that is a delta IL, in ampere is, right? Peak to peak source current ripple they have asked. You can check the circuit operation, you will understand the source current. Yes. Source current and inductor current both are same or different? Both are same only, right? So let me write here. The chopper feeds a resistive load from a battery source. MOSFET with switching frequency is 250 into 10 to the power 3 hertz with a duty ratio D is equal to 0.4. All elements in the circuit are assumed ideal. L value given, supply voltage given, capacitor given, resistance given, load resistance. The average source current in amperes means IS average we need to find. Okay. And the peak to peak ripple current. Second bit, peak to peak source current ripple. Okay. So it is like a delta IL we need to find, because you can check source current and inductor current both are same, right? Source current and inductor current are same. So now duty cycle is given, supply voltage is given. Yes, type of the converter is, it is a boost converter. Okay. So can we find here the output current, output voltage? Yes, it is a boost converter. Boost converter. So let me write V0 is equal to 1 upon 1 minus D into Vs. So it is 1 upon 1 minus 0.4 into Vs is a 12. So it is equal to, if you check, 20. Okay, so it is a 20 volt. V0 is 20 volt. Next, so V0 is 20 volt. What about the I0, which is equal to I0? Okay, which is equal to V0 by R, na? 20 divided by this 20. So it is a V0 divided by R. So 20 by 20. So it is equal to 1 ampere. Yes or no? So average value of load current is a 1 ampere. Average value of load current is a 1 ampere. Now, if you recall from the boost converter, okay, we are having the expression that is the relation between inductor current and a load current. Okay, what is the relation? Inductor current IL average is equal to 1 upon 1 minus D into I0, na? Right? So which is equal to 1 upon 1 minus 0.4 into I0, that is a 1, right? So you can check, it is a 1 upon 1 minus 0.4, right? Into 1. So that will give you the IL average. So it is equal to, yes, 1 divided by 0.6, 1.667 ampere. This is your IL average. Now my question is whether IL average and IS average both will be same or different. IL average and IS average both will be same or different. same na, right? Both will be same, right? So which is equal to your IS average. You can check the circuit operation. Okay, you will understand, because when switch is closed, source current and inductor current both are same. When switch is open, again both are same. Okay, so IL average is equal to IS average, so therefore it is equal to 1.667 ampere, right? Next, so this is about the first bit. Second bit, the delta IL. Okay, peak to peak source current triple is nothing but again your peak to peak inductor current triple. That is a delta IL we need to find. So how to find the delta IL? So during T on, can we apply KVL to the first loop only? During T on means it is like a switch is closed. So it is like VL is equal to 12 volt. Yes or no? Right? So let me write during T on. During T on, or T is equal to 0 to T on, you can write. Okay. During T on, VL is equal to VS, and VL is L into DIL by dt is equal to VS is 12 volt. Okay. So therefore I can write it as a DIL means delta IL is equal to 12 into dt divided by inductor L. Okay. So which is equal to 12 into 0.4 divided by inductor L. It is at 100 microhenry. 100 into 10 to the power minus 6 into time. This is the period, na? So this can be written as in terms of frequency 250 kilohertz. So I'm writing it as a divided by 250 into 10 to the power 3. So if you check delta IL, please check the value of delta IL. Yes. Yes, it is 0.192, no? Right. 0.192 ampere. This is your delta IL. That is nothing but peak to peak source current triple. Okay. So, peak to peak source current triple. Right. Okay. So next. Next example. Okay. Yes. The input voltage to the following DC to DC converter is 20 volt and output voltage is 50 volt. Duty cycle ratio is 0.5. RMS value of diode current is, okay, means our task is to find the ID RMS. So first of all, please check. They have given the data. Input voltage is a 20 volt. Output voltage is a 50 volt. And duty cycle D is equal to 0.5. Yes, my question is whether the conduction is a continuous or discontinuous. Come on. Please check first whether the conduction is a continuous or discontinuous. Either here they have not given the value of capacitor. So it is like a capacitor value is sufficiently high so that the voltage across load will be your constant, or the voltage across capacitor will be constant. Okay. So D is 0.5, output voltage 50 volt. So it is a continuous conduction or discontinuous conduction? Yes, it is a discontinuous, na? Right? So it is a discontinuous conduction, right? So let me write here. For D is equal to 0.5 and Vs is equal to 20 volt. V0 is equal to 1 upon 1 minus D into Vs, which is equal to 1 upon 1 minus 0.5 into 20. So it is equal to 40 volt, which is not equal to 50 volt, right? 50 volt means this given. Okay. That is a given V0. Given V0. The meaning is conduction is discontinuous. Okay. So conduction is a discontinuous. So therefore, let me write. So therefore, conduction is discontinuous. Conduction is discontinuous, right? So for discontinuous conduction, what is the V0? We know V0 is equal to beta upon beta minus D into Vs. Na? So V0 they have given it is a 50 volt. So 50 is equal to beta upon beta minus 0.5 into Vs, it is a 20. So from this, please find beta. Please check for beta. Once we get the beta, after that we need to find the IDRMS. Okay, we need to find the IDRMS, right? Please check what is the beta. .833, right? 0.833. Someone is getting beta is 1. How will you please explain how you got the beta is 1? Pratim, please check how it is 3.33. No, beta should be less than 1 only. 0.833, na? Right? 0.833. This is the beta. So now conduction is discontinuous. If you check this waveform, when switch is in a on state, what is the ID? When switch is in a on state, what is the ID? ID is a 0. Yes or no? Right? Because circuit operation, when switch is in on state, current will flow like this. Okay? Capacitor will be like a discharging. This diode will be in a off state. So ID is a 0. When switch is in a off state, ID is equal to your IL. ID is equal to IL. Yes or no? Right? So let me write here. Yes. When switch is on, ID is equal to 0. Let me indicate ID is equal to 0. And when switch is in a off state, it is like ID is equal to same as that of the IL. So can we draw the waveform of ID? Yes, it is like this. T on, or you can see it is a DT, doesn't matter. And this is a beta T, and here it is a T, na? So, right? So this is the waveform of ID. Now our task is to find the RMS value of this. Okay, RMS value of this waveform. So for that we need to find, yes, we need to find the peak value of this thing, right? Peak value of this one. So let me write this peak value is like a IL max only, na? This peak value is like a IL max only. Now, how will be the waveform of IL? How will the waveform of IL? If you check the IL waveform, it will be like this. Discontinuous conduction. So IL is like this. This is again IL max. Okay, so you can check here. Yes, in this case, this is like a DT, this is like a beta T, and this is a T. Okay, now if I want to find the IL max, right? Now suppose when switch is in a on state, if I apply KVL to the loop, I can write it is a plus VDC minus EL into DIL by DT is equal to 0. And what is the DIL? Change in the inductor current. Inductor current is changing from 0 to the IL max. Okay, so let me write here. During T is equal to 0 to T on. During T is equal to 0 to T on. Yes, what is happening during T is equal to 0 to T on? Yes, here you can check. Switch is in a on state. VL is equal to VS only. Okay, or VDC. Let me write as VDC or VL. Okay, so VL is L into DIL by DT, which is equal to VDC. So now from this DIL is nothing but IL max na, because inductor current is changing from 0 ampere to the maximum value. Okay. So can I write it as IL max minus 0, that is nothing but DIL, is equal to VDC into DT, means duty cycle D into T. That is a T on na, DT means change in the time, that is a T on, divided by your inductor L. Right. Now you can check, in order to find the IL max, we need to know the value of T. We need to know the value of T. VDC they have given, no problem. VDC they have given, it is a 20 volt. Okay. Next thing is duty cycle D, we know, okay, it is equal to 0.5. L also we know, it is equal to 20 microhenry. But whether they have given the T, no, they have not given the T, right? So by using this expression, we cannot find the IL max. Okay, so let me write as switching frequency is not given. Switching frequency is not given, okay, as switching frequency is not given. So therefore can I with by using this expression, we cannot find IL max. So please try to understand, right? If switching frequency we know, then definitely we can find by IL max. Okay, but now how to find the IL max? Let us understand here. Okay, so now you can check, we're having the ID waveform, we're having the IL waveform, right? ID and IL waveforms we're having, right? Now during DT to beta T, yes, whatever the waveform of IL max we are having, the same waveform we are having for ID also. Okay, so now can I say that the average value of this one, I'm saying average value of this. Okay, so ID average I'm saying, because if you check, if we are having the ID average, if I want to find before that, if I want to find the IL average, suppose this is the IL average, let me write this as a IL average. IL average is nothing but what? Average value of the inductor current. So from 0 to DT, IL average is also having the same magnitude. DT to beta T also, IL average is having the same magnitude. Okay. So can I say that? Yes. Can I say that IL average during DT to beta T is nothing but yes, average value of your ID here from DT to beta T only I am saying. From DT to beta T only I am saying. Okay. So can I write it as ID? Please listen. Yes. So can I write ID average, right? ID average. Okay. Yes, here it is. ID average, that is average value of the diode current. Okay. Is equal to, yes, we know it is, I am finding only over this, right? So that is the area under this divided by the full time. Okay. So area under this is nothing but your, yes, 1/2 into IL max into beta minus D into T divided by T, na? Right? So this T will get cancelled. Okay. Now this is your ID average. Okay. Now ID average means we are having this term. ID average means we are having this term, right? That is the average value of the diode current, and diode current is non-zero only during this interval. Okay. Now can we find the IL average also? Can we find the IL average? So before that, yes, IL average, let me check here. IL average is equal to, I can write it as a area under this, okay, plus area under this divided by total time. Okay. IL average is equal to full area under the triangle. So it is like a 1/2 into beta T into IL max, right, divided by total time T. So TT will get cancelled. So therefore IL average is equal to 1/2 into beta into IL max. Okay. This is our IL average, and this is the ID average expression. So let me write it as ID average is equal to 1 by 2 into IL max into beta minus D. Okay, this is the ID average we're having. Right now, can we find the IL average expression so that we can find the IL max expression? Okay, so that we can find the IL max expression, right? So yes, after T ID is 0. After T ID is 0, right? After T the same thing will repeat. Okay, after T the same thing will repeat. Let me correct it. It will repeat like this. Okay, so now can we find the IL max first? Can we find the IL max first? We know V0, we know I0, V0, it is equal to 50 volt. We know the V resistance is 50 ohm. So can I find the I0 first? Yes. So I0 we can find I0. Let me write I0. I0 is equal to V0 divided by R, which is equal to 50 divided by 50, which is equal to 1 ampere. Now I0 is a 1 ampere, which is equal to your I0 average, which is equal to capital I0, which is equal to capital I0 we are having, right? Now, yes, if you check the circuit here, when switch is in a on state, when switch is in a on state, it is like a capacitor is discharging. Okay, capacitor is discharging. Your I0, that is the load current. Okay, load current is equal to 1 ampere. When switch is in a on state, when switch is in a on state, it is like whatever the current flowing here, the same current is flowing here, same current is flowing here. Okay, so as I0 is a constant current, as I0 is a constant current, so can I say that when switch is in a off state, this branch current is a 1 ampere? Yes or no? I am saying average current again. I am saying because I0 we consider it is a constant, doesn't matter. Okay, so when switch is in a off state, when switch is in a off state, can I say that average current flowing through the inductor, average current flowing through the diode is equal to 1 ampere? Please listen it carefully, because when switch is in off state, what is happening? Current is flowing in this branch, current is flowing in this branch. And what is the average current flowing through the load? Average current flowing through the load is 1 ampere. Means when switch is in on state, at that time also current flowing through the load is 1 ampere. When switch is in an off state, at that time also current flowing through the load is 1 ampere. Now if the current flowing through the load is 1 ampere, so can I say that during when switch is in an off state, when switch is in an off state, that is from dt to beta t, that is from dt to beta t, can I say that whatever the average current flowing through the diode is equal to average current flowing through the load is equal to average current flowing through the inductor? It is equal to what? It is equal to 1 ampere. Are you getting the point, right? I am saying that when switch is in an off state, that is from dt to beta t, average current flowing through the diode is equal to what? Your average current flowing through the load, that is equal to 1 ampere. That is equal to 1 ampere. Are you getting the point? Okay, I am repeating. So first of all, we have calculated the V0. V0 they have given, R they have given. So we have calculated the I0 value. So I0 is 1 ampere. So please try to understand here. I0 1 ampere means it is like a current flowing through the load is constant. Here they have not given the value of capacitor. The meaning is capacitor is sufficiently high so that the voltage across capacitor will be maintained constant. That is nothing but the load voltage is maintained constant. Okay. So now if the load voltage is maintained constant, if the load voltage is maintained constant, is like, yes, if the current load voltage V0 is constant, so your I0 is also constant, that is a 1 ampere. That we have calculated. So if this current is 1 ampere, means definitely current flowing through the diode, yes, average current flowing through the diode is also equal to your 1 ampere only, is also equal to your 1 ampere only. So can I write it as I0 is equal to, yes, I0 is equal to, let me write it as, yes, yes. So I0 is equal to V0 by R is equal to 1 ampere. So same thing I am writing, therefore, whatever for ID, whatever for ID we wrote here, yes, is equal to here. For ID average, we have written this thing, 1 by 2 into IL max into beta minus D. Okay, so let me write it as, therefore, I0 is equal to 1 by 2 into IL max into beta minus d into t divided by t. This will get cancelled out, tt. Okay, so this is equal to 1 ampere, which is equal to 1 by 2 into IL max we need to find into beta minus d. Beta is 0.833 and d is 0.5. Okay, so if you check here, IL max is equal to 0.333. It is a 6 ampere, right? So it is a 6 ampere. IL max is a 6 ampere. Okay, now so our task is to find the ID RMS. Okay, ID RMS. Please check how we have calculated the I0. I have written during dt to beta d. If you check, right, during, if I0 is constant now, means in this circuit, if you check, yes, when switch is in an off state, current here flowing will be constant, that is 1 ampere only. So whatever the current that is flowing through the diode, that is also equal to 1 ampere. But that is your, like, the average current, that is like the average current only. Okay, so here that is equal to your, from IL max we have calculated IL max is 6 ampere. Now if IL max is 6 ampere and we are having the ID waveform like this, this is a time t 0 dt beta t, this is t, and we are having this type of waveform. Now this is like a 6 ampere. IL max is a 6 ampere. Now for this waveform, whether we are having the expression for ID RMS value of this waveform, yes, we know it is equal to under root this square, yes or no, divided by 3 into beta minus d, okay, into t divided by t. Okay, so into beta minus d, right? Into t. Same thing during the first chapter, we are having the expression for how to find the RMS value of this type of waveform. Okay, so it is like under root a square divided by 3. After simplification, we have written here 3 into, yes, this pulse width, okay, or the function time, right, divided by your so that is the pulse time divided by your function time. So beta minus d into t. So if you check, it is equal to under root 36 divided by 3 into beta minus d, 0.8333 minus 0.5 divided by, you can check, it is, yeah, divided by t naught, tt will get cancelled. So if you check, it is equal to under root 12 into 0.333, 2 ampere, no? It is 2 ampere. Right? So, yes, capacitor current here, we are simply neglecting it. Please try to understand. When switch is in an off state, let me write here. When switch is in an off state, so can I say that ID is equal to IS plus I0? ID is equal to, sorry, IC plus I0. This is IC, this is I0, and this is ID. Next, simply neglect the capacitor current because they have not mentioned anything regarding the capacitor. Okay, so it is like, assume the capacitor is like a highly inductive, okay, and your capacitor voltage will be constant, right? So now you can check here, can I say that ID is equal to I0? But this is only during this interval, na? This is only during this interval, right? So if during that interval, if your I0 is 1 ampere constant, so can I take that ID is also having the value 1 ampere, right? So that's why I have written at one side ID average expression, at left side I have equated it to the 1 ampere. I have equated to the 1 ampere, right? So it is like ID average is equal to your I0 average. So this indicates ID average is equal to I0 average. So ID average is 1 ampere. So therefore your I0 average is also equal to 1 ampere, right? For in this expression, sir, from where this 3 is there, okay, it has came, okay. So for that, refer the chapter number 1. In the chapter number 1, at the beginning only, we have discussed the average and RMS value expressions of various waveforms. Na? So in that, we discussed this type of waveform also. With the magnitude, we consider it as a capital A. And we had an expression like under root A square divided by 3 into, yes, means this time, okay, or this duration divided by your one function duration, right? So that is beta minus D into T by T, right? Same thing. So yes, for divided by 3, please refer chapter number 1. Yes, IC average is 0. Right. Yes. So means here the switching frequency is not given. So that's why we need to simplify it in another way. If they would have given the switching frequency, okay, then it is like a straightforward question. Is this clear? Right? Okay. So next one. A boost converter has an input voltage of VDC 6 volt. The average output voltage V0 is equal to 15 volt and average load current I0 is equal to 0.5 ampere. The switching frequency is to 20 kilohertz. If L is equal to 250 microhenry and C is equal to 440 microfarad, determine the duty cycle and various parameters they have given. So it is a boost converter. Input voltage is given. It is a VDC is equal to 6 volt. Average output voltage V0 is equal to 15 volt. Average load current I0 is equal to 0.5 ampere. Switching frequency Fs is equal to 20 into 10 to the power 3 hertz. If L is 250 microhenry, and C is equal to 440 microfarad. Determine the duty cycle. Okay, so first bit is finding the duty cycle. Yes, so VDC given, V0 given, so we can find the duty cycle directly. So first, for boost converter, V0 is equal to 1 upon 1 minus D into VDC. So it is a 15 is equal to 1 upon 1 minus D into VDC. That is a 5, right? Sorry, 6. So it is a 6. So therefore, please check the D. Yes, D is equal to 0.6, right? Yes, 0.6. Next, the ripple current of inductor, that is a delta IL. So how to find the delta IL? Now here they have not given the circuit diagram, but we need to recall the circuit diagram of the boost converter. Right? In the boost converter, can we write during 0 to T on VL is equal to VS? Yes. So I can write during T is equal to 0 to T on VL is equal to VS. Okay, because switch is closed, right? And VL is equal to VS. So what is VL? I am writing here L into DIL by dt is equal to VS or VDC. Instead of VL, let me write it as a VDC. Okay, so therefore we can write it as L into DIL, that is nothing but your delta IL, which is equal to VDC into dt divided by L, right? Divided by L. So which is equal to 6 into duty cycle is 0.6. I'm writing this T in terms of frequency divided by F into this term. F they have given It's a 20K and 250 micro. Okay. 20 into 10 to the power 3 into 250 into 10 to the power minus 6, right? So please check what is the delta IL. Point 0.72, 0.72 ampere, right? This is the delta IL. Next bit, the peak current of inductor. Peak current of inductor. Now delta IL we know. Next we need to find the peak current of inductor. So how to find the peak current of inductor? So for that check, I0 they have given it is a 0.5. And for the boost converter, we know IL average is equal to 1 upon 1 minus D into I0. Okay, so let me write third bit. IL average is equal to 1 upon 1 minus D into your I0. So it is equal to 1 upon 1 minus 0.6 into what is I0? They have given it is a 0.5, 0.5. So it is equal to 0.5 by 0.4. Yes, it is 1.25. No? This is the IL average. So if this is IL average, what is the IL max peak inductor current? That is IL peak. IL max is equal to IL average plus delta IL by 2. No? So it is equal to 1.25 plus delta IL 0.72 divided by 2. Yes, it is 1.61. Okay, 1.61 ampere. This is your IL max. Next, the ripple voltage of filter capacitor, that is a delta V0 they have asked me. Okay, delta V0. So how to find delta V0? Delta V0 is equal to delta Vc, na? Which is equal to delta Q by C, right? So what is the delta Q? How we calculated the delta Q in the boost converter? If you recall, it is a I0 into T on, na? Yes or no? I0 into T on we wrote. So it is equal to I0 into T on divided by C, and T on is nothing but dt. I0 into dt divided by C. Okay, so therefore delta V0 is equal to I0 is 0.5 into 0.6 divided by frequency into C. So frequency is to 20K and it is 440 micro. 20 into 10 to the power 3 into 440 into 10 to the power minus 6. Yes, how much? Delta V0. .3 or 0.034? 0.034, no? Right. 0.034. 0.0340. Okay. Volt. This is your delta V0. Next bit, the critical values of L and C. Yes, the L critical and C critical. Fifth bit, L critical and C critical. Either you can directly use the expressions D into 1 minus D square into RT divided by 2. Okay. So D we know it is a 0.6 into 1 minus 0.6 square into R. They have not given the R, but from V0 by I0 we can find the R. It is a 15 by 0.5. No? It is a 15 by 0.5. V0 by I0 will give you the R, right? Divided by 2 into switching frequency. It is a 20 into 10 to the power 3. So please check L critical. (72 microhenry). Okay, 72 microhenry. This is a L critical. And next C critical. C critical. C critical is dt by 2r. 0.6 divided by 2 into 20 into 10 to the power 3 into r. That is a 15 by 0.5. Na? That is a 30. Okay. So please check. I have replaced the t with 1 upon frequency. .5 microfarad, na? 0.5 microfarad. Okay, 0.5 microfarad. This is a C critical, right? L critical is 72 microhenry. C critical is 0.5 microfarad, right? I have replaced this T with 1 by frequency here. Frequency is 20K, right? So yes, L critical 72 microhenry, right? Okay. Next. Yes. So here, a DC to DC boost converter, as shown in the figure below, is used to boost 360 volt to 400 volt at a power of 4 kilowatt. So output power is given 4 kilowatt, okay, which is equal to your input power only. Next, input voltage 360 volt, output voltage is 400 volt. We are having a boost converter. All devices are ideal considering continuous inductor current. The RMS current in the solid state switch, yes, in ampere is, okay. Our task is to find the RMS value of the switch current, RMS value of the switch current, right? So yes, so let us first note the data. Vs is equal to 360 volt, V0 400 volt, T0 is equal to 4000 watt. All devices are ideal considering continuous inductor current, that is like a continuous conduction. The RMS current in the solid state switch, that is the ISW RMS, we need to find, okay. ISW RMS we need to find. L is given, it is equal to 10 into 10 to the power minus 3 Henry. This is a L value, okay. So it is a boost converter, right? Now power is 4000 watt. Power is equal to 4000 watt, right? So here first thing is, can I find the I0 average? Yes, okay. P0 is equal to P0 is equal to V0 into I0. So therefore I0 is equal to P0 upon V0, right? So it is equal to 4000 divided by 400. So it is equal to 10 ampere, right? I0 average is equal to 10 ampere. Now, can we find the duty cycle here? Yes, duty cycle D is equal to, we can find. So duty cycle D. Now, for boost converter, we know V0 is equal to 1 upon 1 minus D into Vs. 400 is equal to 1 upon 1 minus D into 360. So therefore find the value of D. Please check the D value of D, duty cycle D, right? It is 400 divided by 360, and from that find the value of D. Yes, how much? Point 1 or 0.125? It is a 0.1, right? Point 1 duty cycle D. Okay, so D is equal to 0.1, right? 0.1, correct? Yes. So correct. So D is equal to 0.1. Now we know D, we know I0. Can we find IL average? Yes, IL average is equal to, we can write IL average is equal to 1 upon 1 minus D into I0, na? Which is equal to 1 upon 1 minus 0.1 into I0 is a 10. So please check what is IL average. It is like 10 by 0.9. 10 by 0.9. 11.11 ampere, na? 11.11 ampere. Okay, so this is IL average. Now let us find the ISW RMS, right? They asked for the ISW RMS. Now you can check the circuit operation. When switch is in a on state, when switch is in a on state, yes, it is like a IL and ISW, both will be same or different, both will be same. When switch is off, ISW is 0. Yes or no? When switch is off, ISW is 0. So can I draw the waveform of ISW? It will be like this. Zero to dt, d2 to t. Okay, so this will be, the waveform will be like this. It will be increasing from this point and again decreases, right? Okay, so it is changing from your I1 to I2, I1 to I2. Now you can check, or can we approximate this waveform as ISW t 0, 0 to dt and dt to t, right? As like this. How will the waveform of IL? IL waveform is like I1 to I2 during 0 to dt. During dt to t, it is I2 to I1, na? And IL average is like a constant waveform. So same thing, I'm approximating ISW waveform in terms of your IL average waveform. You can check, yesterday we did this same thing. ISW we approximated, right? As that of the IL average waveform. Okay. So now for this waveform, can we find the ISW RMS? So now ISW RMS is equal to 1 by T integration from 0 to dt. It is like IL average into IL average square into dt to the power 1 by 2. RMS na square root of mean of squared value. So if you take IL average is a constant value. Okay, so take it outside. So it is IL average into what? Under root D. Okay, under root duty cycle D. That is under root dt by t. Tt will get cancelled out. That is equal to under root D. So it is equal to IL average into root D. What is IL average? We have calculated, it is a 11.11 into what is the duty cycle? It is a 0.1. So if you check ISW RMS, yes, it is equal to 11.11 into root 0.1. 3.51, right? 3.51. Right? Next. Yes. We'll discuss this example, and after that we'll start the buck boost converter. Okay. So because remaining examples are related to the buck boost converter. Next, a step down chopper operates from a DC voltage source Vs. Please read the statements carefully. A step down chopper means it is like again your step down chopper, whatever we discussed. Okay, operates from a DC voltage source Vs and feeds a DC motor armature with a back EMF EB. So it is like we're having a supply voltage. Okay, next we're having a switch, we're having a diode, after that inductor and a motor. Okay, next feeds a DC motor armature with a back EMF EB. From oscilloscope traces, it is found that the current increases from time tr. Current increases for time tr. Current is increasing for time tr. Falls to 0 over time tf. It is falling to 0 over time tf and remains 0 for time t0 in every chopping cycle, right? Then the average DC voltage across the freewheeling diode is, okay? So let me first draw the circuit diagram. Yes, the circuit diagram will be like this. We're having a supply voltage Vs. Here it is a switch. Here it is a freewheeling diode. And we're having a RLE load. Either you can connect the inductor here, or if not connected, then also no problem. So R, L, because one inductor is already present in the motor circuit. Right? This is like your EB. This is L. This is R. Freewheeling diode D. Right? Or let me write this DF. They have asked for average voltage across the freewheeling diode. Okay. This is like IDF. Voltage across freewheeling diode. I am representing like this. VDF. This is a switch S or SW. IS. So we're having the circuit diagram like this. This is your V0. Here it is a I0. Right? So please note, yes, whatever they have given. A step down chopper operates from a DC voltage source. So we're having the step down chopper. It is operating from a DC voltage source. Next, and feeds a DC motor armature with a back EMF EB. We have considered the back EMF as a EB. Right? Next, from the oscilloscope traces, it is found that the current increases for time TR. Means the current in the circuit is increasing for time TR. Now, current in the circuit, that is nothing but your I0, is increasing for time TR. The meaning is, can we say that when switch is in an on state, it is like current is flowing from source towards the load, inductor go on storing the energy, and I0 will be increasing. Yes or no? Are you getting the point? Okay. So can I draw the waveform like, suppose I0 waveform, if we want to draw, this is time t as they have given. Current increases for time TR. Please listen it. From oscilloscope traces, it is found that the current increases for time TR. Current is increasing for time TR. Okay. So for time TR, the current is increasing. So current waveform will be like this. It is increasing. Okay. Next, it will reach to some peak value. After that, it is given that falls to 0 over time TF. Falls to 0 over time TF. Okay. So it is falling to 0 from this value. It is falling to 0 over time TF means this total from this point to this point. The time is TF. So can I say that this time is like TR plus TF? Please try to understand. This time is TR. This time is TF. So what about this time? It is a TR plus TF. Okay. TR plus TF. Next, falls to 0 over time TF and remains 0 for time T0, and it remains 0 for time T0. The meaning is the current is 0 for a time T0, means from this point to this point where having a time is a T0. And so can I say that this time is like your TR plus TF plus T0, and after that again the same cycle repeats. So please try to understand what they have given. The current is increasing over time TR. After that, it is falling to 0 over time TF, means this time is TR. This time is TF. And this time is T0. This time is T0. Okay. So that's why it is TR here. Here it is TR plus TF. Here it is TR plus TF plus T0. Okay. Now, so this is the about the current. They have given the information of the statements in every chopping cycle. Then the average DC voltage across the freewheeling diode is. Now our task is to find the voltage across the freewheeling diode average value. Okay, so here you can check in this circuit, current is increasing. The meaning is inductor is storing the energy. Yes or no? So can I say that here it is like inductor stores energy. Stores energy. Current is decreasing means inductor releases energy. Inductor releases energy. Yes or no? And after that it is a 0, means it is like a discontinuous conduction we are having. So you can check current inductor will store the energy. It is possible when switch is in on state na. So when switch is in a on state, what will happen? Suppose switch is in a on state, current is flowing from source towards the load through the switch. Inductor is storing the energy. So at that time, what is the voltage across diode? The voltage across diode is nothing but Vs only na. Yes or no? Because diode is like a open circuit. Okay, so can I draw the waveform for voltage across diode? Yes. VDF, voltage across diode. Time t 0, TR, TR plus TF, TR plus TF plus T0, right? So when switch is in a on state, voltage across diode is like a Vs. This voltage is Vs. After that, inductor releases energy. Current is decreasing na. So current will decrease. The meaning is it is like switch is in an off state. Inductor will go on releasing the energy through the freewheeling diode. So when inductor releases the energy through the freewheeling diode, whatever the voltage across freewheeling diode, it is a 0. So that's why here, yes, the waveform of the VDF will be 0 here. After that, you can check current is 0. Current is 0 means it is like a circuit will be at the rest position. So if the circuit is at rest position, the meaning is this diode is also open circuit, this switch is also open circuit. So can I say that the voltage across freewheeling diode is equal to V0? Yes or no? So what is V0? If current is 0 here, what is the V0? V0 is equal to EB na, right? So V0 is equal to EB. So let me write it as it is a EB, right? And after that again the same cycle repeats. So this will be your EB. This will be the EB. Now our task is to find the average value of this VDF. Yes, we can find. This is your TR. This is TR plus TF. And here it is TR plus TF plus T0. Okay. So we can find the VDF average. So therefore, VDF average is equal to, either you can apply integration from 0 to TR this term plus integration from TR plus TF to TR plus TF plus T0, this value divided by total time, or you can find the area, right? In both the ways you'll be getting the same answer. So I'm writing it as in terms of area. So it is a Vs into TR plus EB into this term na. What is this time? This time is like TR plus TF2, TR plus TF plus T0 means it is a T0. Okay. So plus EB into T0 divided by the total time, TR plus TF plus T0, right? So it is a Vs into TR plus EB into T0 upon TR plus TF plus T0, right? So we need to understand here, the current increases means which is in an on state, inductor stores energy. Current decreases, falls to 0 means inductor releases energy. It is possible only when switch is in an off state. And when inductor releases energy, it will release the energy through the freewheeling diode. Okay. And when current is 0 means it is like circuit will be at the rest position, right? So from this we can find the VDF average, right? VDF average. Important thing here, if you check the given circuit diagram and the given options, generally the voltage across the diode, the polarity we mention it as a anode positive, cathode negative. But if you take the polarity like that, anode positive, cathode negative, then you will be getting the waveform of voltage across diode. It will be like a negative we will be getting, right? Minus Vs 0 minus EB. Okay, and that will not match, right? That will not match to your options. Okay, so that's why here we need to consider the voltage across diode polarity is like this. Okay. 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 So we'll take a break here. We'll start at 7:15, right? After the break, we'll discuss about the buck boost converter. Same 14 steps we need to follow. And after that, we'll be discussing about the effect of resistance of inductor, okay, on the performance of your buck boost and buck boost regulators or the converters. And next we'll be discussing the numericals related to the buck boost converter. Okay. Yes, I will discuss all your doubts at the end of the session. So welcome back. Now we are going to discuss the buck boost converter. Okay. Already we discussed about the buck converter and the boost converter. The buck converter is the converter where the output voltage is less than the input voltage. Boost converter is the converter where the output voltage is greater than the input voltage. And now we are going to discuss the buck boost converter, means the single circuit we are having that can be used as a buck converter and the boost converter. Okay, that is a step up and step down, right? Like thing. So let me put the heading buck boost converter. Buck boost converter. Yes. So depending on the duty cycle, it acts as a buck converter or the boost converter. Okay. So circuit diagram. So this is a VS switch, ISW, IS, L, voltage across inductor is VL, diode D, current flowing through the diode is ID, capacitor IC, voltage across capacitor is VC. Just a minute. VC. Please be careful. The polarity of the voltage across the capacitor and current flowing through the voltage across the capacitor and voltage across the load, okay, is like this. This is I0. Why it is a reverse, we are going to discuss. Okay, so this is the buck boost converter we are having. Same, we are having a switch, inductor and a diode. If you check in the buck converter, the inductor was connected or placed at the load side. In the boost converter, inductor was placed at the source side. In the buck boost converter, here inductor is connected at the middle. Okay, that is at just like a shunt branch. Okay, so now here, if you check the circuit operation, when switch is in a on state, it is like inductor go on storing the energy, diode will be in a off state. Okay, current flowing through the inductor will be in a downward direction. So this is the direction, IL current direction. When switch is in an off state, inductor go on releasing the energy like this. Okay, inductor releases the energy like this. Okay, so when inductor releases the energy, it is like capacitor will be charging. Capacitor will be charging. So here you can check, when inductor releases the energy like this, na, in the anti-clockwise direction, the direction of the current flowing through the capacitor will be in upward direction. Na? So that's why the capacitor voltage polarity will be plus here and a minus here. As capacitor is connected in parallel with the load, so that's why the load voltage polarity is also lower terminal positive, upper terminal negative. Please try to understand this point compared to that of the other circuits. Okay, whatever we know, whatever till now we have discussed, in that case we consider the load voltage is nothing but upper terminal positive, lower terminal negative. But in the buck boost converter, it is different. Okay, because when inductor releases the energy, connection is such that when inductor releases the energy, the current will be flowing in the anti-clockwise direction. Na? So that's why capacitor will be charging, means it is in the upward direction, current will be flowing. Okay, so due to the polarity is a plus here, minus here it is a plus and minus, right? So this is the thing. Otherwise, if we want to charge the capacitor like this, the diode will not allow the current in the clockwise direction, right? So next, so this is the buck boost converter circuit diagram. So let us follow the steps. First step is when switch is in an on state, that is for t is equal to 0 to t on, switch is in an on state. It is like switch is in short circuit, diode is in a open circuit mode. Okay, so let me draw the circuit. When for t is equal to 0 to t on, switch is in a on state. Switch is in a on state. Okay, so when switch is in a on state, the circuit diagram will be like this. Vs, switch is short circuit, inductor stores energy, diode open circuit, and here we are having a capacitor, right? RC. Okay, this is a L, this is a Vs, SW, and a diode. Next, we are having current is Is. This current is ISW. Here it is IL. This voltage is VL. Diode current ID. Capacitor current IC. Capacitor voltage VC. Load voltage is V0. Right? Load voltage is V0. Now, yes, can we say that here inductor is storing the energy? Yes, inductor stores energy. Stores energy. So during this mode of operation, if we apply KVL to this loop, we'll be getting VL is equal to VS. Yes or no? VL is equal to VS. That is voltage across inductor is equal to source voltage. Next, what about the current? If we apply KCL at this node X, whatever the current here, the full current is yes, whatever the current here, the same current will flow here. Whether the sum part of the inductor current will be flowing here? No, because you can check current in this branch. In this loop, if you consider this branch current is 0, so definitely this branch current will be also 0 ampere. Okay, in the loop you can check, if you consider this as a loop current, if this current is 0, means definitely this current is also 0. Okay, so I can write it as KCL at node X. KCL at node X. So it is like 0 is equal to, this is like I0. Okay, 0 is equal to IC plus I0. So therefore IC is equal to minus I0. IC is equal to minus I0, right? So now IC is minus I0, VL is equal to VS. Now can I write IS, ISW, IL all are same? Yes. So further I can write IS is equal to ISW is equal to IL, all are same, right? What about the inductor current? Inductor is storing the energy. So that's why inductor current will change from I1 to I2. It will go on increasing, na? It will increases because inductor is storing the energy, right? Next, so this is when T is equal to 0 to T1. Next, ID is equal to 0. One more thing, let me write it as ID also equal to 0 ampere. Okay, ID is 0 ampere. Next, for T is equal to T on to capital T. T on to capital T. It is like switch is open. Okay, switch is open. So when switch is open, the circuit will be like this. Supply voltage. Here it is a inductor. Inductor releases energy now. Inductor will go on releasing the energy, right? So current flowing through the inductor is in this direction only. Diode, you can check in this case. When inductor releases the energy, diode will be in a conduction mode. Okay, so we'll be having the circuit like diode is in a conduction mode. Here it is a capacitor and here it is a load resistor R. Right? So we're having the C here, R here. This voltage is V0. This voltage is VC. Current here is ID, IC, I0, ISW, IS, and this is a VS, right? So now you can check here. Inductor is releasing the energy. Inductor is releasing the energy. Okay, so here let me write L releases energy. Inductor L releases energy. So now when inductor releases energy here, yes, you can check. Here it is an open circuit, which definitely current here is 0. This is current 0, no? ISW current is 0 because open circuit. So definitely current in this branch is also 0. So whatever the current here is, the same current will flow here. That is a IL, right? Now can I apply KCL at this node X? It is IL is equal to IC plus I0. Okay, so KCL at node X. Yes, KCL at node X. So it is IL is equal to IC plus I0. So therefore I can write it as IC is equal to IL minus I0, right? Similarly, what about the VL? You can check. Can we apply KVL to this loop? KVL to this loop. It is like a minus VL minus V0 is equal to 0, na? Right? So minus VL minus V0 is 0 means VL is equal to minus V0. Okay, so let me write VL is equal to minus V0. Further, whether ID and IL both are same or different, you can check here. Current is ID and the same current is flowing here. So I can say that IL and ID both are same. Okay, so IL is equal to ID, both are same. Next, ISW, IS 0. Okay, ISW and IS both are 0. So ISW is equal to IS is equal to 0 ampere is equal to 0, right? So this is when switch is in a on state and when switch is in a off state. Next, now can we write the Holt second balance equation? Yes, next step is a Holt second balance equation. Holt second balance equation. Yes. VL during on state of the switch, that is on time, into T on, plus VL during off time into T off is equal to 0. Okay. So what is the voltage across inductor during on time of the switch? It is a Vs, na? We have written VL is equal to Vs. So let me write it as a Vs into T on means dt, plus voltage across inductor during off time. It is equal to minus V0. It is equal to minus V0. So let me write it as minus V0 into T off. T off means T minus T on is equal to 0. So therefore it is Vs into dt plus, or let me write it as minus V0 into 1 minus d into T is equal to 0. No? So can I write it as therefore Vs into dt is equal to V0 into 1 minus d into T. T will get cancel out. So therefore V0 is equal to d upon 1 minus d into Vs, right? This is the expression for output voltage. Now Vs is a constant voltage, right? So can I say that this V0 is nothing but your V0 average value of output voltage. Here you can check. This is a d upon 1 minus d into Vs, na? If your duty cycle d is less than 0.5, I'm writing if d is less than 0.5. If d is less than 0.5, then what will happen? You can check V0. Suppose d is equal to 0.25. 0.25 upon 1 minus 0.25. So 0.25 by 1 minus 0.25 means it is 0.25 by 0.75. 0.25 by 0.75 means it is like 1 by 3, na? So output voltage is equal to 1/3 of Vs, right? So that is like yes, V0 is a less than a Vs. Okay, so V0 will be less than Vs. The meaning is it is like a buck converter. It is like a buck converter. You can check for any value of a duty cycle which is less than 0.5. Yes, you will be getting V0 is less than that of a Vs only. V0 is less than that of a Vs. Okay, so it is like a buck converter. This is a buck converter. Next, for or if d is greater than 0.5, if duty cycle d is greater than 0.5, for example, suppose d is equal to 0.75. If d is 0.75, so it is like 0.75 upon 1 minus 0.75. So it is 0.75 divided by 1 minus 0.75 means 0.25. So 0.75 by 0.25 means it is like a 3, na? So V0 is 3 into Vs. So therefore, can I write V0 is greater than Vs? The meaning is it is like a boost converter. Boost converter. Are you getting the point? Okay. So for d less than 0.5, our converter behaves as a buck converter, and for d greater than 0.5, the converter will behave as a boost converter. Okay, converter will behave as a boost converter, right? So this is V0 expression, which is equal to d upon 1 minus d into Vs. Next, let us discuss the ampere second balance equation. Ampere second balance equation. Ampere second balance equation. So it is IC during on time into T on plus IC during off time into T off is equal to 0. Okay. So during on time, what is the IC? If you check, we had 0 is equal to IC plus I0. No? So IC is equal to minus I0. IC is equal to minus I0 into T on is a dt plus IC during off time. it is like IL is equal to IC plus I0. We have written. So IC is equal to IL minus I0. Okay, IL minus I0 into T off. T off means it is like a T minus T on is equal to 0. So therefore I can write minus I0 into dt plus IL minus I0 into 1 minus d into t is equal to 0, right? So from this I can write it as a minus I0 dt, and this is like a plus I0 dt, or let me write first I0 dt plus IL into 1 minus d into t minus I0 into 1 minus d into t is equal to 0. Okay, so you can check minus I0 t minus minus plus I0 dt. This plus I0 dt, this minus I0 dt, it will get cancelled out. Okay, so this will be like IL into 1 minus d into t, which is equal to, I'm writing it as I0 into t. Yes or no? So therefore tt will get cancelled out, and there we can write it as a IL is equal to 1 upon 1 minus d into I0. I0 is a constant current we are having. Okay, so this is like your average value of inductor current, IL average. Expression for IL average. Please be careful. Expression for average value of inductor current is 1 upon 1 minus d into I0, right? Which is same as that of whatever we discussed in a boost converter also. Okay, in a boost converter also, right? So 1 upon 1 minus d into I0. This is your IL average. Next, yes. Now, can we draw the waveforms of the yes, IL, ID, ISW, VC, etc. Okay, so waveforms, let me draw. How is the IL waveform? This is like a T on to T, T to T plus T on, right? And so as we discussed, during 0 to T on, inductor stores energy, na? Inductor stores energy. So here, when inductor stores energy, so definitely current flow through the inductor go on increasing. Okay, so IL waveform will be like this. It increases from I1 to I2. Okay. Next, during T on to T, inductor releases the energy. So IL waveform will be decreasing. Next, again it will be increasing and again decreasing. Okay. So this is the waveform of IL. IL average waveform will be like this. Average value of the inductor current. It will be passing through the center point. Okay. Exactly center point. This will be like your IL average. IL average. Okay. So next, delta IL means, let me indicate the delta IL here. Yes. So this is the delta IL, right? This is your delta IL. Okay. So IL waveform. Next, can we draw the waveform of IC? Or let me draw first I0 waveform. You can check the waveform or the expression. IL is equal to 1 upon 1 minus d into I0 we are having. Okay. So from this, whether our I0 will be greater than IL or less than IL. You can check. I0 is equal to 1 minus d into IL. Na? So some fraction of average value of inductor current is nothing but your load current. Yes or no, right? So please be careful here. The load current is less than that of your inductor current, average value of the inductor current. Okay, so I0 waveform. Let me draw the I0 waveform. Right? Next, IC waveform. We can draw the IC waveform. T on T plus T on, right? So this is T on T plus T on. Yes. During 0 omega, during T is equal to 0 to T on. What is IC? IC is equal to minus I0, right? We discussed it. So IC is equal to minus I0. So it is a minus I0. This is minus I0, right? So during T on to T, IC is equal to IL minus I0. You can check during T on to T we have written, during T on to T, IC is equal to IL minus I0. Okay, so IL minus I0 means, yes, this waveform IL minus this, right? So IL minus I0 waveform will be like this. Again, the negative here. So this is like your IL minus I0. Okay, I0 is a constant current, right? So T on to T. Next, what about the VC waveform? From IC waveform, we can draw the VC waveform. T on T, T plus T on, right? So during 0 to T on, you can check IC is negative, right? IC negative means capacitor will discharge. Yes or no? Capacitor will discharge. And IC positive means capacitor will charge. Okay, so capacitor is discharging and charging. So the waveform will be like this. So capacitor discharges like this, and again it charges during T on to T, and again it discharges, right? So you can check the waveform. Again it discharges. So it will be having this type of waveform. So the difference between these two, this point and this point, is nothing but your delta VC, na? This is nothing but your delta VC. Delta VC. Okay. Similarly, we can draw the waveform of IS T on. This is a T plus T on. Right? So what is the IS waveform? If you check the circuit operation, yes, when switch is in a on state, IS, ISW and IL all are same. Okay, so IS waveform will be same as that of your IL waveform, right? And again, IS and ISW waveform both are same. When switch is in on state, IS, ISW both are same as that of the inductor current. When switch is in a off state, IS and ISW both are zero. Okay, so let me draw the waveform of IS and ISW. I will indicate here because both are same. Okay, so the waveform will be like this. It will be same as that of your inductor current. And again here it is a 0. Again the same repeats. Correct? So this is changing from I1 to I2 and same as that of your IL, same as that of the inductor current, right? IS and ISW waveform. Next. Okay. Yes. So now, what about the ID waveform? Can we draw the ID waveform? Diode current waveform. During 0 to T on, come on, what is the diode current? During 0 to T on, what is the diode current? Yes. During 0 to T on, you can check the diode current is 0. Na? We have discussed the circuit operation, right? Yes, it is 0. Dinesh, you are saying, sir, why it is not touching to 0, right? Because we are discussing this continuous now first. After that, we discuss that just continuous and next the discontinuous like thing. Okay, so yes, so ID is 0. During 0 to T on, ID is 0. Next, T on to T, ID is same as that of the inductor current. Na? You can check inductor releases the energy, right? And your diode will be in a conduction mode. So during T on to T, ID and IL both will be same. So IL waveform we are having, it is a decreasing. Na? So it is like this. And again it is a 0. So this type of waveforms will be getting. It is same as that of the IL. Same as that of the IL, right? Next, it is like a I2 here. And here it is a I1. Now, one by one, let us discuss the parameters. So first of all, let us find the delta IL. Okay, delta IL. So ripple in inductor current. ripple in inductor current, that is delta IL. Okay, delta IL. So you can check during t is equal to 0 to t on. During t is equal to 0 to t on. Yes, we're having the circuit like switch is in a on state. VL is equal to VS. Yes or no? We're having VL and VS both are same. So I'm writing VL is equal to VS. What is VL? L into DIL by dt. L into DIL by dt is equal to VS na. So this can be written as L into. How the inductor current is changing during 0 to t on? It is changing from I1 to I2. Okay, so can I write DIL is changing the inductor current I2 minus I1 divided by dt, change in the time. Time is changing from 0 to t on. So it is like a t on minus 0, which is equal to Vs, right? So let me write it as a, therefore L into I2 minus I1 is nothing but delta IL divided by t on, that is nothing but dt, is equal to Vs. So I can write it as delta IL is equal to Vs into dt divided by L. Okay, Vs into dt divided by L. Is this clear? So more the value of duty cycle, more will be your delta IL. More will be the delta IL. Okay, or further I can write it as delta IL is equal to Vs into d divided by F into L in terms of frequency. Right? So in order to reduce the delta IL, reduce the delta IL means it is like for getting the constant IL, yes, we require a more value of inductor. Higher the value of inductor, lesser will be your delta IL. Okay, at the same time, higher the value of frequency, lesser will be the delta IL. Okay, so in order to reduce the delta IL, we need to increase the L as well as we need to increase the F, that is the switching frequency. Right? Next, as duty cycle increases, delta IL increases. Okay, and it is maximum at d is equal to dmax. Right? Next, so this is the delta IL. Now can we find the IL average expression? Yes, IL average value of inductor current, IL average is equal to, you can check the IL waveform we have drawn. It is like this. So it is like I1 plus I2 by 2. Okay, I1 plus I2 by 2. It is I1 plus I2 by 2. Okay, I1 plus I2 by 2. Next, IL max, maximum value of inductor current, which is equal to I2, is equal to IL average plus delta IL by 2 na, same as that of the previous case, right? IL mean is equal to I1 is equal to IL average minus delta IL by 2, same as that of the previous case. Yes or no? You can check here. IL waveform we are having. IL average means this red line, right? So this is the IL average. So if I add delta IL by 2 into the IL average, I will be getting I2, right? That I2 is nothing but your IL max. And if I subtract delta IL by 2 means nothing but 50% of this part. Okay, if I subtract delta IL by 2 from IL average, I will be getting I1. I will be getting the I1, right? So here IL mean and IL max, and that is the IL average we have written. Okay. Next, further, yes, can we write the source current average value? Average source current. Now in our case, source current and switch current both are same. Okay, so I'm writing average source current, which is equal to average switch current. I'm writing it as an average switch current also. Okay, so how is the waveform of source current or switch current? During 0 to t on, switch is on. So waveform is same as that of your inductor current. So like this. After that it is 0. Right? So this is changing from I1 to I2. I1 to I2. Okay, so further we can approximate this as IL T0 T on T, right? So this is like your IL average, correct? This value is the IL average. So what is the, sorry, this is the IS or ISW, no? Yes. What is the IS average or ISW average here? Yes, I'm writing here IS average is equal to ISW average is equal to 1 by T integration from 0 to T on. It is IL average into dt. So it is equal to IL average into T on by T. T on means dt divided by T. Dt will get cancelled out. So it is a D into IL average, right? So duty cycle D into IL average, right? Next, what about the diode current average value? Diode current average value. Average diode current. So ID waveform we have already drawn. T on T. Diode current is non-zero from T on to T only, na? And it is same as that of the inductor current. Yes or no? It is like this. I2, I1, and here 0 here, and here it is also 0, right? So further I can approximate this as ID T on T. This can be represented as IL average. Okay, so now here, yes, we can write ID average. ID average is equal to 1 by T integration from T on to T. It is a IL average into dt, na? So it is equal to, we can write IL average divided by T into T minus T on. So this can be written as 1 minus D, na? 1 minus duty cycle D into IL average. This is your ID average. ID average, right? So average value of diode current, average value of switch current we have written. Next, ripple in capacitor voltage. Ripple in capacitor voltage. So ripple in capacitor voltage, right? That is a delta VC, which is equal to delta V0, no? Yes. How to find delta VC or delta V0? It is a delta Q by C. Now we can check the VC waveform. Yes. Here it is, we are having the maximum voltage of VC max. Here it is a VC min, na? So the change in the capacitor voltage, that is VC max minus VC min, is nothing but your delta VC, na? Right? And it is changing from 0 to T on. Suppose consider the time that is 0 to T on. So corresponding to 0 to T on, if you check the IC waveform, 0 to T on, it is a minus I0. So if I take the area under this rectangle, it will give the delta Q. It will give the delta Q, right? Delta Q. So can I say that delta Q is equal to I0 into T on, right? So it is a I0 into T on. Let me write, it is equal to I0 into T on divided by C. So further we can write, therefore delta VC, which is equal to delta V0. Delta V0 is equal to I0 into T on means dt divided by C. This is your delta VC, right? Ripple in capacitor voltage. Now here you can check, as duty cycle D increases, ripple in capacitor voltage also increases, and it will be maximum at D max, at D is equal to D max, right? So next, now let us find the critical inductance and critical capacitance. So critical inductance that is L critical. L critical. Okay. We discussed the L critical means it is the value of inductor in the circuit such that IL is like a just continuous. Yes or no? IL is a just continuous. Okay. So IL waveform for L is equal to L critical. It will be like this. So it will be increasing during on state of the switch, and next it will be decreasing na, and it will be again increase. This is a just continuous. Yes or no? This is like your I2, or let me write it as IL max is equal to I2. Okay, so this is a just continuous. Right, IL is a just continuous. Next. Okay, next. So it is a just continuous. Now L critical. So can I say that IL average is equal to delta IL by 2? So delta IL means in this case this is delta IL. Okay. So IL average, let me draw the IL average also. Yes. This is the IL average. IL average. So can I say that? Yes, Shravan Kumar. Do you want to say something?
I will ask at the last note session.
Yes. Okay. So IL average we are having, right? So now can I say that IL average is equal to delta IL by 2? Yes or no? Right? IL average is delta IL by 2. Now further, what is the IL average in terms of I0? We know it is a 1 upon 1 minus D into I0 is equal to delta IL by 2. What is delta IL? We have written delta IL expression here. Please check. Delta IL is equal to Vs into dt by L. Vs into dt by L. So let me write it as Vs into dt divided by L is nothing but now these two as it is divided by L. Okay. So now you can check here. Can I replace this I0 with a V0 by R? Yes. So I can write it is a 1 upon 1 minus D into V0 by R is equal to Vs into dt divided by 2 into L. 2 into L. Right? Now here further what we can do, I can replace this D V0 with D upon 1 minus D, okay, into Vs. So it is like 1 upon 1 minus D as it is into this 1 by R as it is. I'm going to replace this V0 with D upon 1 minus D into Vs, na, which is equal to Vs into dt divided by 2L. So you can check D, Vs, it will get cancelled out. Okay, so therefore from this can I write? Yes, 1 upon 1 minus D square into R is equal to T upon 2L, and this L is nothing but your L critical. Okay, L critical. So therefore I can write L critical. L critical is equal to 1 minus D square into RT divided by 2, na? This is your L critical. If we want to write R critical, okay, if we want to write R critical, then it will be also R critical is equal to, yes, 2 into L upon 1 minus D square into T. 2L upon 1 minus D square into T. That will be your R critical, right? So, next. So L critical is over, R critical is over. Now C critical value of capacitor. Okay, C critical. So C critical. Right? C critical. So corresponding to C critical, yes, just like here, we had IL average is delta IL by 2. So we'll be having VC average is equal to delta VC by 2. Okay, VC average is equal to delta VC by 2. So therefore, we can write it as a VC average means again V0 na is equal to delta VC. Delta VC we have written the expression for delta VC we are having. Yes, I0 into dt by C. I0 into dt by C. I0 into dt divided by C. So it is a 2 into C. So further I can write this. I can replace this V0, okay, with a d upon 1 minus d into Vs. D upon 1 minus d into Vs, which is equal to I0 can be replaced with V0 by R into dt upon 2 into C. Right? Further we can write it as a this V0 can be replaced, okay, yes, in terms of your d upon 1 minus d into Vs, but ultimately it will be getting cancelled out. So let me keep it here V0 as it is, so that your V0 will get cancelled out. Okay, so this is equal to V0. This V0 will get cancelled out. Okay, so no need to replace your V0 in terms of Vs. Okay, next, so therefore we can write C critical. Therefore C critical is equal to dt by 2R. dt by 2R, right? This is the C critical, right? So next, so this is about the continuous conduction. This is about the continuous conduction. Dinesh, what you want to say? Sir, we get it from formula, but why we use those formulas? Means
Sir, just one thing, sir. In this critical capacitance, why are we taking this delta VC by 2?
where critical capacitance.
Yes, sir. This delta VC by 2. How does it come, sir?
Actually, the thing is, your when L is equal to L critical, at that time your IL is like a just continuous, and when C is equal to C critical, your capacitor voltage will be like just continuous.
Okay, sir.
Means if you check the VC waveform, here we are having the VC waveform. Yes, here it is, right? It is like a continuous only, I have shown here.
Yes, sir.
So if C is equal to C critical, your VC will be like this point will be reaching to 0.
Okay, sir.
So it will be discharging, reaches 0, and from the same point again it charges.
Okay, sir.
Right?
Yes, sir.
Okay.
Okay, sir.
Next. Yeah, Gopal, maximum, yes, duty cycle for maximum ripple. I informed you the ripple is proportional to the duty cycle, na? The ripple is proportional to the duty cycle, right? So if duty cycle is maximum, your ripple will be maximum, right? So same thing I have written here also. In the IL, you can check, yes, delta IL is proportional to D. So here as duty cycle increases, delta IL increases, and it is maximum at D is equal to D max, right? So same thing here. Means if you are thinking that to apply that maxima theorem here, no, we cannot apply the maxima theorem. If you apply here maxima theorem na, for this delta VC, you can apply the maxima theorem, right? You will be getting D 1 is equal to 0 like thing. Okay, so whether 1 is equal to 0, no, na, right? So that's why in a boost converter also, if you check, we have not used that maxima theorem because it is directly proportional to the D, na, right? Okay, so L critical and C critical we are having. Next, if the conduction is discontinuous, then what to do? Okay, so if conduction is a discontinuous, conduction is discontinuous, right? So conduction is discontinuous means, suppose we are having IL here, 0 to T on, or let me write it as a dt. Dt is nothing but T on only. Suppose this is beta T and this is a T, na? Yes, it is IL increases and again decreases, reaches 0, and again it is having the 0, right? So it is a discontinuous conduction. Okay, it is a discontinuous conduction, IL max. Okay, so here if you check during T is equal to 0 to dt, for T is equal to 0 to dt, switch is closed. Okay, switch is closed. So if switch is closed, what is VL? Recall the circuit diagram. If switch is closed, VL is equal to VS, na? Right? So VL is equal to VS. Next, for T is equal to dt to beta T. dt to beta T. Switch is open. Inductor releases energy. Okay, inductor releases the energy through the diode. Okay, at that time, what is VL? VL is minus V0. VL is equal to minus V0. This is till only beta T. After beta till T, inductor is not having the energy to release, right? So that's why circuit will be at the rest position, right? So it is like your VL will be 0. Now, can we have, yes, apply or use that Holt second balance equation? Yes. So here, Holt second balance equation. Holt second balance equation. So let me write it as Holt second balance equation. So VL during on state of the switch into T on plus VL during off state of the switch into T off, means we need to consider only this time, that is beta T minus dt. Beta T minus dt is equal to 0. So therefore we can write it is a VL, it is a VS during on state, na? It is VS into dt plus VL during off state is a minus V0 into beta minus d into T is equal to 0. So therefore I can write Vs into dt is equal to V0 into beta minus d into T. T will get cancel out. So therefore, yes, I can write, therefore Vs into d is equal to V0 into beta minus d. So therefore V0 is equal to d upon beta minus d into Vs, right? D upon beta minus d into Vs, right? So this is your V0 average. V0 average, average value of voltage, output voltage, okay, for the discontinuous conduction, for the discontinuous conduction. Okay, for the continuous conduction it is a d upon 1 minus d. Okay, but here it is d upon beta minus d. So in which case we'll be getting the more V0 average. In the discontinuous conduction we'll be getting the more V0 average, because here in the numerator, in the denominator we're having beta minus d. Beta is less than 1, na? Right? So beta minus d will be less than your 1 minus d. Okay, so that's why V0 average will be more. Okay, so let me write, yes, V0 average for continuous conduction, for continuous conduction, let me write as V0 CCM. It is d upon 1 minus d we have written into Vs, and V0 average for discontinuous conduction, for discontinuous conduction, yes, it is a V0 DCM is equal to, we have written d upon beta minus d, d upon beta minus d into Vs. So you can check beta is less than 1. Okay, so therefore your V0 DCM is greater than V0 CCM, right? Yes. So this is about the buck boost converter, right? Next, now we are going to discuss the effect of internal resistance of the inductor, okay, on the respective converter. Okay, so effect of internal resistance of inductor. Effect of internal resistance on internal resistance of inductor. Okay, we're going to discuss. Let us first discuss for the buck converter. Okay, so before that, so far whatever we discussed, in that case we consider the inductor as a pure inductor. Okay, means the pure inductor means it is not having the any internal resistance, that is R is equal to 0. But in practical case, yes, the inductor is having some internal resistance, small value, but definitely that will be a non-zero, right? So how that resistor affects on the performance of the converter, that we are going to discuss, and we are going to derive the V0 average expressions for buck converter, boost converter, and buck boost converter by considering the effect of that small resistor R also. Okay, so let me indicate first. Yes, we're having a inductor. It is like a small resistor, that is the internal resistance, and this is the inductor L. So we're having a small resistance R, and here it is a inductor L. Means whatever we discussed till now, in that case we use the inductor means only this part, right? We neglected the internal resistance, but in practical case the internal resistance is present. Okay, internal resistance is present, right? So now let us discuss what will happen. Definitely current flowing through the inductor is a IL. Current flowing through the inductor is a IL, right? Let me yes, represent the voltage across this part is VL, and definitely according to the Ohm's law, the voltage across this part will be like IL into R. Okay, IL into R. Now let us discuss the effect on first buck converter. We'll be getting the modified V0 average expression. Okay, so buck converter. So recall the buck converter circuit. We're having the switch here, right? Here it is a diode, and here it is the inductor, right? Now inductor means consider R and L also here. Capacitor is present, and here it is a load. You can consider the load is resistive. Small resistor, this is the inductor L. So that will be your practical inductor now, right? Inductor, this voltage as VL, and this current is IL. Okay, C R, this is a V0 and R0, right? So when switch is in a on state, right? So can I write when switch is in a on state? It is like it is in a on state. So apply KVL to the outer loop. It is like a plus Vs minus R into IL minus VL minus V0 is equal to 0. Yes or no? Right? So can I write it as when switch is in on state? Okay, apply KVL to the outer loop. So let me write it as plus Vs minus R into IL minus VL minus V0 is equal to 0. So therefore let me write R into IL, yes, minus VL, okay, sorry, plus VL is equal to Vs minus V0. Okay, Vs minus V0, right? Consider as equation number 1. Okay, this is when switch is in a on state. Okay, switch is in a on state. Next, when switch is in a off state, when switch is in a off state, you can check this circuit. When switch is in a off state, okay, means it is open. It is like inductor will go on releasing the energy. Diode will be in a conduction mode, na, right? So can we apply KVL to this loop? Yes, it is a minus R into IL minus VL minus V0 is equal to 0. Okay, so KVL to loop. KVL to loop. I'm writing it as a minus R into IL minus VL minus V0 is equal to 0. So therefore I can write it as R into IL plus VL is equal to minus V0. Consider it as equation number 2. Right? Now can I write the whole second equation during the on state of the switch? Okay, can I write the whole second equation during the on time of the switch? Okay, so whole second equation during t is equal to t on, that is 0 to t on, right? T is equal to t on means 0 to t on. Okay, so here when t is equal to t on means we are having this expression na? So this is like a voltage at left side, right hand side also we are having the voltage. If I multiply both the sides with a t on, I will be getting it as a R into IL plus VL into t on na? Is equal to, at the right hand side it is a Vs minus V0 into t on. Vs minus V0 into t on. Consider as equation number 3. Similarly, can we write the whole second equation during the t is equal to t on to capital T? Yes, whole second equation during t is equal to t on to capital T. T on to capital T means this second equation we need to multiply with the off time. Okay, because during the off time we're having this, right? R into IL voltage, this also voltage, this is also voltage, right? We're having the equation. So I can write R into IL plus VL into T off is equal to Vs minus V0. Sorry, not Vs minus V0. It is a minus V0 only, na? Right? It is a minus V0 only. So it is a minus V0 into T off. Consider it as equation number 4. Now, can we add equation 3 and equation 4? Yes, let me add equation 3 and equation 4. So if I add the equation 3 and 4, I am getting it as RIL into T on, and here it is RIL into T off. So can I write R into IL into T on plus T off plus, I am writing left hand side first. Okay, VL into T on plus VL into T off. Let me write VL T on plus VL T off is equal to what? Vs minus V0 into T on. Vs minus V0 into T on minus V0 into T off. So now you can check what this term indicates, right? What this term indicates. Let me create it as a plus. Okay, what this term indicates? It is a voltage across inductor during on time into T on plus voltage across inductor during off time into T off. What is the voltage across inductor during on time into T on plus voltage across inductor during off time? It is a 0, na? Yes or no? That is average voltage across inductor. It is a 0 only. Yes or no? Right? So average voltage across the inductor is a 0. So let me write it as VL average. This indicates VL average, which is equal to 0. So this term will become 0. This term will become 0. So we'll be having only R into IL into T on plus T off, na? So T on plus T off means T. Okay, is equal to, I can write it as Vs minus V0 into T on minus V0 into T off. T off is nothing but it is like a T minus T on. T minus T on. Okay, so further I can write it as R into IL into T is equal to, yes, it is like a Vs minus V0 into dt minus V0 into 1 minus d into T. So this can be written as Vs minus V0 into d minus V0 into 1 minus d, and I am taking T outside. Here it is R into IL into T. You can check this T will get cancelled out, right? So R into IL is equal to, yes, Vs minus V0 into d minus V0 into 1 minus d. Now you can check here. This is we're having a buck converter. Output side is a constant voltage. Supply is also constant voltage. So you can check here. If this is constant, this is also constant, this is also constant. V0 and Vs were having constant, right? So can I say that at the left hand side, whatever the IL we're having, it is nothing but your IL average only. Please try to understand. Can we say that this IL is nothing but IL average only? Yes or no? Right? So this is nothing but your IL average, because you can check at the right hand side, we're having only one fixed value, right? For any value of the duty cycle D, we'll be getting only one value at the right hand side, because we're having the Vs is fixed, V0 is a constant voltage, D is the duty cycle, that is just a number. Okay, so you can check right hand side, we're having the only constant value, that is a number. So that R is also constant value we're having. So IL is nothing but we will be getting only one number, that is a constant value. That is nothing but your IL average here. That is nothing but the IL average. Yes.
Hello, sir.
Yes.
I have a doubt that if means I have not changed any parameter, only R value is changes to R critical. And in the previous
where you are saying R is changed to R critical?
Let's suppose in buck converter or any boost converter, any type.
Okay. Can we
Okay.
discuss it at the end?
Okay.
Right. Yes. So this IL is nothing but your IL average. So let me write it as R into IL average. Please have some patience. We'll discuss all your doubts at the end. Okay. Is equal to, I am writing it as a Vs into D minus this V0D. This is plus V0D will get cancelled out. Okay. So it is like only V0. Only V0 will remain. So R into IL average is equal to Vs into D minus V0. Next, what is the IL average? If you check, we're having the buck converter. We're having the buck converter. And in the buck converter, we know IL average is equal to I0 average, na? Right? IL average is nothing but the I0 average. So let me write it as, therefore, R into IL average is nothing but I0. That is the I0 average, which is equal to Vs into D minus V0. Vs into D minus V0. Right? So further I can write I0 is nothing but V0 by R. Right? So it is R into V0 by R, which is equal to Vs into D minus V0. So further we can write it as, can I shift this V0 to the left hand side? Yes. So it is R into V0 by R plus V0 is equal to Vs into D. So we can write it as, this can be written as V0 into 1 plus R upon R is equal to D into Vs. So therefore, V0 is equal to D upon 1 plus R upon R, okay, into Vs. This is your V0. This is the V0. That is nothing but your V0 average. V0 average. So suppose in the numerical, if they ask the question like inductor, we are having, suppose the value they have given some like 2 millihenry or 1 millihenry. And if they say that the internal resistance of the inductor is non-zero, that is suppose given the values like 0.1 or 0.3 ohm, etc. Okay, then we need to use this expression in order to find the V0 average. Please be careful. Is this clear? Right? So V0 average is D upon 1 plus R upon R into Vs. Here capital small r is nothing but internal resistance of the inductor. Capital R is nothing but the load resistor. Okay, and D is the duty cycle. Okay, Vs is the supply voltage. Right? Okay, so if you recall, in the continuous conduction mode without a small r, that is without considering the value of internal resistance of the inductor, we got V0 average is equal to D into Vs. Here it is D upon 1 plus R upon R. So can we say that this denominator will be more compared to that of the previous case? So we'll be getting the V0 average will be lesser. Yes or no? V0 average will be getting the lesser. Okay, slightly lesser, right? Slightly lesser, because your R value, capital R value will be higher than that of your this small r value, right? Small r value, right? Okay. So far they have not asked the question, right? but be prepared. Yes, next let us discuss the effect on the boost converter, right? On the boost converter. Boost converter. So same, recall the circuit diagram of the boost converter. In the boost converter, at the supply side, we're having the inductor. Here it is a Vs. Here we are having a switch, diode, capacitor, and a load, right? Vs, L. Now with series, in series with the inductor, we need to consider the internal resistor also, right? R, L, right? Switch, diode B, capacitor C, R. This is a V0. This is a I0, right? This current is like your IL. This voltage is VL. This is a small r, right? So when switch is in an on state, so during t is equal to 0 to t on, t is equal to 0 to t on, yes, switch is in an on state. Switch is in an on state. So if you check here, when switch is in an on state, we can write it as a KVL to this loop, right? KVL to the loop 1. Let me write KVL to loop 1. So it is like plus Vs minus R into IL minus VL is equal to 0. Yes or no, right? So therefore I can write R into IL plus VL is equal to Vs. Consider it as equation number 1. Similarly, we can write for t is equal to t on to capital T. T on to capital T. So T on to capital T means switch is open, right? Switch is open. So simply inductor go on releasing the energy through the diode D. Diode D will be in a conduction mode. Apply KVL to the outer loop. So we'll be getting it as a plus Vs minus I into R minus VL minus V0 na, is equal to 0, right? Same thing, whatever we discussed in the previous case, right? We're discussing here. The only thing is here, yes, this small r is getting added. Small r is getting added, right? So it is a IL into R, IL into R, right? The drop across that small resistor. So here I can write therefore IL into R plus VL is equal to, let me write it as a Vs minus V0. Consider it as equation number 2. Again the same step, hold second balance equation during on, T on. Hold second balance equation during T on, right? So we can write it as a, during T on we're having this step, R into IL plus VL into T on is equal to Vs into T on. Okay, consider it as equation number 3. Similarly, we can write hold second balance equation during T off. Hold second balance equation during T off. Right? So we can get it as R into IL plus VL into T off is equal to Vs minus V0 into T off. Further, we can add equation 3 and 4, right? Equation 3 plus equation 4. So if you check at the left hand side, R into IL into T on, R into IL into T off. So let me write R into IL into T on plus T off. Okay. Next, plus VL into T on plus VL into T off. Yes. So which is equal to, we can write it as Vs T on plus this term as it is, right? So Vs into T on plus Vs minus V0 into T off. So further we can write it as again the same thing, VL into T on plus VL into T off. That is the average voltage across the inductor. That is Volt second balance equation. Okay. So which is equal to 0. VL average, which is equal to 0 volt. Okay. So therefore I can write it as RIL into T is equal to Vs into T on means dt na, plus Vs minus V0 into T off means T minus T on. Right? So therefore I can write R into IL into T is equal to Vs into D, let me write, plus Vs minus V0 into 1 minus D, because T on is dt na, so I am writing into T as it is. So T will get cancelled out. Further it is R into IL is equal to Vs into D plus Vs minus V0 into 1 minus D. Again this IL is nothing but again IL average. Okay, so R into IL average is equal to Vs into D plus V0 into 1 minus D. Right? So here I am writing IL average. Can we replace this IL average in terms of I0? It is a 1 upon 1 minus D into I0. Okay, so let me write it as R into 1 upon 1 minus D into I0 is equal to VSD. Here it is, and it is minus VSD. It will get cancelled out. So it is Vs minus 1 minus 2 V0, right? V0. So further we can write I0 can be replaced with V0 by R. Okay, so R upon 1 minus D into V0 by R is equal to Vs minus 1 minus D into V0. No? Okay, so next this is V0, here it is also V0, right? Bring all the V0s at one side. So it is like R upon R into 1 minus D into V0 plus 1 minus D into V0 is equal to Vs. So therefore I can write it as a V0 into R upon R, sorry, small r, upon R into 1 minus D plus 1 minus D na, is equal to Vs. So this can be written as taking the cross multiplication. Okay, so it is R plus R into 1 minus D square. So therefore V0 into small r plus R into 1 minus D bracket square divided by R into 1 minus D. This is R into 1 minus D is equal to Vs. Yes or no? I have simply yes cross multiplied. Okay, so divided by R into 1 minus D. So next further we can take capital R common. Okay, so it is like V0 into, let me take the capital R common. So it is R into, this can be written as small r by capital R plus 1 minus D square divided by this R into 1 minus D is equal to Vs. So RR will get cancelled out. So therefore V0 into R upon R plus 1 minus D is equal to Vs. So therefore V0 is equal to 1 minus D upon R upon R plus 1 minus D brackets, right? So this is your V0 expression, which is nothing but V0 average. V0 average, right? So yes, 1 minus D upon R plus 1 minus D bracket square into Vs, right? So you can check if small r is 0. If small r is 0, then it is like V0 average is equal to 1 minus D upon 1 minus D bracket square na, into Vs. So 1 minus D will get cancelled out 1, and only thing is 1 upon 1 minus D will be getting, right? So V0 average is this thing. Next, Now we can check here. Okay, Prajit. Okay. Yes. So now here V0, we are having this type of term, and whereas if you consider in the buck converter, we had a V0 is equal to, it is proportional to directly D. So in the buck converter, we can say that in order to get the more V0 average, yes, D should be more. But in this case, yes, if we want to find the value of duty cycle D, for getting maximum V0, okay, then what will the value of that D max? Let us find. Okay, so let me write here. Yes, duty cycle for maximum V0 average, right? Means now we are going to write the expression of the duty cycle for getting the maximum V0 average, Now let me copy this. V0 is equal to 1 minus D upon R plus 1 minus D bracket square, okay, into Vs, right? So now in order to get the maximum V0 average, okay, so can I, if I differentiate this V0, because this is V0 average only, okay, if I differentiate this V0 with respect to duty cycle D, and if I equate it to 0, right, then from that I can get the required value of the duty cycle for getting the maximum V0 average. Okay, so let me differentiate dV0 by dd and equate it to 0, right? So let me write d by dt of this term, the term is here 1 minus D upon R plus 1 minus D bracket square, okay, into Vs, and we need to equate it to 0. Yes or no, right? So it is like U by V we need to use, okay, U by V we need to use, right? So yes, so it is, therefore I can write it as R by R plus 1 minus D bracket square into, this is a V na, into differentiation of this 1 minus D. What is differentiation of 1 minus D? It is a minus 1, right? Next, minus this term as it is, 1 minus D as it is, into differentiation of this term, right? Differentiation of this term. What is differentiation of R by R? It is a constant, so it is 0. Differentiation of this term, it is a 2 into 1 minus D into minus 1 na, and divided by this V square na, this square. So it is R upon R, let me write, plus 1 minus D bracket square and its square, equated to 0, right? Yes or no? Now this term into 0, if I shift this term to the right hand side, that will be 0 only. Okay, so I can write it as R by R plus 1 minus D bracket square into minus 1 minus 1 minus D into square na, into 2 into minus 1 is equal to 0. Can I shift this term to the right hand side? Yes. So therefore R by R plus 1 minus D bracket square into minus 1 is equal to, I'm shifting this term to the right hand side. So it is like a 1 minus D bracket square into 2 as it is, into minus 1. So this minus 1 will get cancelled out. So therefore I can write it as R upon R plus 1 minus D bracket square is equal to 2 into 1 minus D bracket square na, right? So further I can shift this 1 minus D bracket square to the right hand side. So it will be like 2 1 minus D bracket square minus 1 minus D bracket square. So 2 1 minus D bracket square minus 1 minus D bracket square means only 1 minus D bracket square will remain. So therefore R by R is equal to 1 minus D bracket square. So therefore I can write it as under root R upon R is equal to 1 minus D na, right? So therefore I can write it as D is equal to 1 minus under root R upon R. And what this D indicates, this D is nothing but your duty cycle corresponding to maximum V0 average. Okay, so it is a D max, which is nothing but duty cycle corresponding to maximum V0 average, right? So duty cycle corresponding to the maximum V0 average. Is this clear? Right? Okay. So this is about the boost converter. Okay. Next, for the buck boost converter, again we need to follow the same steps. Okay, I'm giving the direct expression. You can simplify it by same steps we need to follow. Whatever for buck converter we have done, whatever for boost converter we have done, the same steps you can follow, and you will be getting the expression whatever I'm giving now. Okay, so for the boost converter, sorry, buck boost converter, for the buck boost converter, yes. Yes, I'm writing this V0 average by considering the effect of inductor resistor. Inductor resistor, that is small r is present. Okay, so it is equal to D into 1 minus D upon, yes, R upon R plus 1 minus D bracket square into Vs. You can simplify it, we'll be getting the same answer. This is your V0 average. V0 average by considering inductance resistor, internal resistance of inductance. Internal resistance of inductance. Internal resistance of inductor, right? So this is about the effect of internal resistance of inductor, okay, on the buck boost and buck boost converter. So you can check with the effect of a small r. Actually, there is a decrease in the overall V0 average, okay, by a small amount, by a slightly decrease, we can see, right? Next. Now we are going to discuss the numericals related to the buck boost converter. Okay, buck boost converter. Yes. Yes. Yeah. In the following circuit, the ideal switch yes is operated. Is my voice breaking? Please check once. Yes, it is better to remember, right? Memorize these expressions. Specifically, as long as your that effect of small r is considered. Okay. Yet they have not asked, but they can ask, right? So please be prepared. Right? Voice is clear, na? Yes. Okay. Thank you. So, now, in the following circuit, the ideal switch yes is operated at 10 kilohertz. The circuit is operated in steady state at the boundary of continuous and discontinuous. Yes, it is a boundary between continuous and discontinuous. Find the on time of switch and peak current through the switch, right? So we need to find the on time and the peak current, right? So let me first note this data. First thing is, which converter is this one? Buck boost or buck boost? Yes, it is a buck boost converter, na? Switch here, inductor is at the yes common branch, and here it is the diode. Okay, so it is a buck boost converter. So let me write here, switching frequency f is equal to 10 kilohertz, 10 into 10 to the power 3 hertz. Next, the circuit operated in steady state at the boundary of continuous and discontinuous. Okay, so it is like a just continuous case we are having. Next, on time of the switch we need to find, right? That is a T on. And second thing we need to find peak current through the switch, ISW peak. Now whether the ISW peak and your IL peak, both will be same or different? Come on, whether ISW peak and IL peak both will be same or different? Check when the switch is in a on state. When switch is in a on state, current is flowing into this circuit na, in this loop. So your switch current is equal to inductor current. Inductor go on storing the energy. So inductor current increases from I1 to I2, right? So it is a just continuous. So it is inductor current will increase from 0 to maximum value, right? So maximum value of inductor current is nothing but the maximum value of switch current, right? So IL peak is equal to your ISW peak. IL peak is equal to ISW peak, right? So capacitor they have not shown here, right? But they have indicated the load voltage is constant. Okay. So indirectly the meaning is, yes, load voltage is constant means it is like your capacitor is present already. Okay. But not represented. Doesn't matter. Okay. So let me write here. Yes. On time of the switch we need to find. Duty cycle they have not given. Okay. So now my question is, for just continuous conduction, can we use the V0 average expression of continuous conduction? Yesterday we discussed this thing. For the just continuous conduction, can we use the expression of V0 average, whatever we have derived for the continuous conduction? Yes, no? Yes, because just continuous means it is like a continuous only. Okay, just continuous like a continuous only. So here I can write V0 average is equal to D upon 1 minus D into what? It is a supply voltage, that is a VDC. So V0 average is 500. Be careful here, polarity again plus minus. Same thing, same polarity is whatever we discussed, okay, during the circuit analysis. So 500 is equal to D upon 1 minus D into VDC, it is 100 volt. So from this, can we find D? Yes. So therefore I can write phi is equal to D upon 1 minus D. So therefore phi minus phi D is equal to D. So therefore D is equal to how much? It is a 5 by 6, na? Yes, 5 by 6. So it is equal to 0.833, right? 0.833. So duty cycle is equal to 0.833, right? Okay. So next, so duty cycle is given, frequency, duty cycle we have calculated, frequency is given. So can we find the on time? Yes. So now on time of switch is equal to T on is equal to D into T, na? Right? So this can be written as D is 0.833 and T is nothing but 1 by frequency. So it is 1 upon 10K, 1 upon 10 into 10 to the power 3. So if you check, it is 0.833. So 83.33 na microsecond. Correct? Next, second bit, they are asked the ISW peak. So let me draw the waveform of ISW waveform will be like this. It is a just continuous they have given, na? So it is like your ISW peak, which is equal to IL max, na? Which is equal to I time T, right? Next, so it is same as that of the inductor, na? So during T is equal to 0 to T1, T is equal to 0 to T1. Can we apply KVL to the loop? You can check here. Switch is in on state. The circuit will be like this. Okay, current will be flowing like this. So can I say that VL is equal to VS? Yes. So during t is equal to 0 to t on, VL is equal to Vs. And what is VL? L dIL by dt is equal to Vs. Vs is 100 volt, na? They have given, right? 100 volt. So therefore I can write it as L. Let me write it as DIL is nothing but IL max minus 0, right? Is equal to dt, means this is 100 as it is, into dt means d into t, that is the on time. Okay, divided by L. Is this clear? Right. So therefore IL max is equal to 100 into duty cycle d is 0.8, that on time. Okay, so you can write that on time as it is, divided by frequency, it is a 10k, and into inductor value, it is a 100 micro. 100 into 10 to the power minus 6, right? So therefore what is IL max? Yes, please check IL max. $83.33, right? It is 83.33. $833. Yes, 83.33 ampere, right? Okay. Yes, 83.33 ampere, right? Okay. So this is the IL max. Again, it is equal to your ISW peak, na? So therefore, peak switch current is equal to IL max is equal to 83.33 ampere, right? 83.33 ampere. Next, yes, the input voltage to a buck boost converter is a 20 volt. Input voltage to a buck boost converter is 20 volt. Assume that the capacitor is large to treat output voltage is constant of 60 volt. Output voltage is 60 volt. The switch is operating at 50 kilohertz with a duty ratio of 0.6. Average value of inductor current is, our task is to find the IL average, right? IL average we need to find. Okay, so yes, first of all, let us note the data. Input voltage VES or VDC, you can say 20 volt. Output voltage is equal to 60 volt. D is given, it is a 0.6. L is given, it is a 20 microhenry. Right now, from V0 input voltage, output voltage, and duty cycle, please check whether the conduction is continuous or discontinuous. Come on, please check whether the conduction is continuous or discontinuous. So for D is equal to 0.6 and Vs is equal to 20 volt. What is a V0 for continuous conduction? It is D upon 1 minus D into Vs. No? So it is 0.6 upon 1 minus 0.6 into Vs, that is a 20. Yes, it is. Discontinuous, but what is the value? 0.6 by 0.4, no, into 20. So it is a 30 volt, right? So it is a 30 volt. So conduction is a discontinuous, right? So which is not equal to 60 volt, right? Given V0 average. Given V0. So therefore conduction is discontinuous, right? Conduction is discontinuous. let me write conduction is discontinuous. Yes. So for discontinuous conduction, what is the expression we're having? Yes, we're having V0 average is equal to D upon beta minus D na, into Vs, right? So V0 average they have given, it is a 60 volt, is equal to D, duty cycle is 0.6 upon beta minus 0.6 into what is Vs, it is a 20. So from this find beta. Yes, please check the beta value. Come on, what is the beta value? 0.8, right? Beta is a 0.8. How the 1.2 you are getting? Beta should be less than 1 only, right? Beta is 0.8, 0.8, right? So beta is 0.8. Now beta we know it is a 0.8. Now can we draw the IL waveform? Yes, IL. Time t 0. This is like a dt. This is a beta t, and this is time t. Okay, so IL waveform is like this. It is increasing, decreases, reaches 0, and again 0. Right? So same thing. Right? Now can we find this value? IL max. Our task is to find IL average, na? Average value of inductor current. So average value of inductor current means area under this divided by total na time, right? So IL max how to find? So during 0 to dt, during t is equal to 0 to dt, that is nothing but t on. Switch is in a on state. So when switch is in on state, VL is equal to VDC na, right? So let me write VL is equal to VDC or VS, you can say. VL is L into DIL by dt, which is equal to VDC. So this can be written as, from this I am writing DIL is nothing but change in the inductor current. It is changing from 0 to IL max, na? So it is like a IL max is equal to VDC into dt, that is on time, divided by inductor L. Yes or no? So therefore it is VDC given, it is a 20 volt into duty cycle D 0.6 divided by L 20 microhenry, 20 into 10 to the power minus 6 into, check for frequency, yes, frequency they have given or not, 50 kilohertz, right? So 50k, so 50 into 10 to the power 3. Yes, so from this find IL max. Yes, it is 12 ampere, right? It is a 12 ampere. IL max is equal to 12 ampere. Now IL max is 12 ampere. So what is the average value of IL? So let me write IL average is equal to area under this triangle. It is a 1/2 into IL max into beta. Okay, so 1/2 into IL max into beta t divided by t na. T will get cancelled out. So it is 1/2 into IL max is 12 into beta, it is 0.8. So you can check, it is 4.8, right? 4.8. Next. Yes. A buck boost converter has an input voltage VDC is 12 volt. The duty cycle D is equal to 0.6 and the switching frequency is 25 kilohertz. For the inductance L is equal to 250 microhenry and for the capacitance C is equal to 220 microfarad. For the average load current I0 is equal to 1.5 ampere. Determine, yes, the average output voltage, peak to peak ripple current in inductor, right? Same things they have asked again. Yes, these are for buck boost converter. So, yes, what is VDC? 12 volt. Duty cycle D is equal to 0.6. Switching frequency F is equal to 25 into 10 to the power 3. Inductance L is equal to 250 microhenry. Filter capacitance C is equal to 220 microfarad. I0 is given, it is a constant current 1.5 ampere. Determine the first bit average output voltage V0. Yes, V0 we need to find. Buck boost converter. What is V0? D upon 1 minus D into Vs. Okay, so it is 0.6 upon 1 minus 0.6 into Vs. 12 volt, right? Yes, how much? $18 volt. Okay, so it is a 18 volt V0. So V0 is equal to 18 volt. Second bit, the peak to peak ripple voltage delta V0. How to find the peak to peak ripple voltage? It is a delta Q divided by C, na? Right? Delta V0 is equal to delta Q by C, right? So second bit, delta V0 is equal to delta Q by C. Recall the IC waveform, right? Delta Q is like IC into I0 into T1. Okay, so it is a I0 into T1 means dt divided by C. So please check delta V0, which is equal to I0 they have given. It is 1.5 into duty cycle, that is 0.6 divided by C. Capacitor value 220 microfarad into frequency. It is a 25 K. Yes, therefore delta V0. Come on. Please check the delta V0 value. .1636, right? 0.1636 volt, na? 0.1636 volt. Third bit, the peak to peak ripple current in inductor. Yes, how to find the peak to peak ripple current in an inductor? Delta IL. During on time, apply KVL, na? VL is equal to VS, right? So during T on, VL is equal to VS. Okay, so if VL is equal to VS, it is like L into DIL by dt is equal to VS, right? So it is L into DIL is nothing but delta IL divided by dt is equal to Vs. Okay, so let me write as delta IL. Therefore, delta IL is equal to Vs into dt divided by L. Yes, please check the value. Delta IL. Vs is given, dt is given. Yes or no? So Vs is 12 volt into duty cycle D is 0.6, na? Yes. Divided by L into F. L is 250 microhenry. 250 into 10 to the power minus 6 into frequency 25 K. Yes, please check. $1.152, right? 1.152 ampere. This is a delta IL. correct? Next bit, the peak current of the switch, ISW peak. Come on, ISW peak. I think it is a fourth bit. ISW peak. How to find the ISW peak? Whether it will be same as that of your IL peak, whether ISW peak will be same as that of the IL peak, yes, no? Yes, right? Yes. So how to find the IL peak? IL average plus delta IL by 2, na? What is IL average for buck boost converter? 1 upon 1 minus D into I0, na? Right? So 1 upon 1 minus D into I0 plus delta IL by 2. Yes, 1 upon 1 minus 0.6 into I0 they have given. I think it is 1.5, right? Delta IL we have calculated 1.152 divided by 2. Yes. Please check. Imtiaz, please check your answer once. Yes, it is 4.326, right? 4.326 ampere. Okay. So this is your ISW peak. And next, critical value of inductor and capacitor, no? L critical, C critical, right? So how to find L critical and C critical? Yes, we are having expression is R into 1 minus D bracket square into T divided by 2. Or you can write IL average is equal to delta IL by 2. Okay. So R is not given. We need to find R is, we need to replace R with V0 by I0. Okay. So let me write it as V0 by I0. Into 1 minus 0.6 bracket square divided by 2 into frequency 25K, na? What is V0? $18 and I0 is 1.5, na? Right. So it is 18 upon 1.5. 1 minus 0.6 bracket square divided by this term 50 into 20. Yes, how much? 38.4 microhenry. L critical. Okay, and next C critical. So C critical, it is equal to dt by 2R, 0.6 divided by 2 into V0 by I0 into frequency. It is 0.6 divided by 2 into 18 upon 1.5 into frequency 25K. Yes, so it is C critical. One microfarad, right? 1 microfarad. Okay. Next, Next example. This one variable. Okay. Okay. Yes. We'll discuss two numericals and then we'll stop. Okay. Yeah. The input voltage VDC of the buck boost converter shown below varies from 32 volt to 72 volt. Assume that all components are ideal, inductor current is continuous, and output voltage is ripple free. The range of duty ratio D of the converter for which the magnitude of the steady state output voltage remains constant at 48 volt is. Okay, so please listen what they have given. First thing is your input voltage is varying between 32 to 72 volt. So lower limit for the input voltage is 32 volt, upper limit is 72 volt. But irrespective of the variation, okay, in the input voltage, our converter is giving the output voltage as 48 volt. Okay, and they have asked what is the range of the duty cycle. Very simple question. Let me write here. VS1 is equal to 32 volt. VS2 is equal to 72 volt. 72 volt. Right? And V0 is equal to 48 volt only. Now, our task is to find the duty cycle. So you can check when input voltage is 32 volt, then also converter is giving the output as 48 volt. When input voltage is 72 volt, then also the converter is giving the output as 48 volt. Okay. So can we find the first when Vs is equal to Vs1, that is 32 volt, and output is 48 volt, what is the duty cycle value? After that, we can find when Vs is equal to Vs2, that is 72 volt, and output voltage is 48 volt, then what is the duty cycle value? Okay, so we'll be finding two duty cycle values, and accordingly, yes, we can get the idea. Okay, so let me write first. Yes, Vs1 is equal to D upon 1 minus D into, sorry, V0, na? V0 is equal to D upon 1 minus D into Vs1. So what is V0? 48 is equal to D upon 1 minus D into 32. So corresponding to this, find D, duty cycle D. Come on. It is like 32 plus 48, that is 80. Okay, 80 into D is equal to 48. So 48 by 80. So it is 0.6, right? Let's check once. 0.6, right? 3 by 5. 0.6. Similarly, V0 is equal to D upon 1 minus D into Vs2 now. So it is 48. V0 remains same, 48 only. So it is D upon 1 minus D into Vs2, that is 72. Now please find the value of D. So 48 plus 72, 120 D, okay, is equal to 48. So 48 divided by 120. Is a 0.4, right? 0.4. Yes. So you can check here. One duty cycle is less than 0.5. Sorry, one is less than 0.5. Second one is a greater than 0.5. So can we say that? Yes. 48 volt output voltage. If the input is in the range of 32 to 48, then our converter will behave as a boost converter. If the input is from 48 to 72 volt, then the converter will behave as a step down, that is a buck converter. Okay, so what is the range of duty cycle? It should be from 0.4 to 0.6. Yes or no, right? So range of duty cycle, let me write. So range of duty cycle. Yes. 0.4 less than or equal to D less than or equal to 0.6. Okay, so 0.4 to 0.6 means it is 2 by 5 to 3 by 5, right? Option A. Next, In the circuit shown, all elements are ideal and the switch yes is operated at 10 kilohertz. Okay. And 60% duty ratio. The capacitor is large enough so that the ripple across it is negligible and at steady state acquires a voltage as shown, right? That is a 75 volt they have given. That is V0 is 75. Next, the peak current in amperes drawn from the 50 volt DC source is, right? Our task is to find the IS peak, right? IS peak we need to find. Yes, simple question. F is equal to 10 into 10 to the power 3 hertz. Duty cycle is given, it is a 0.6. Vs is 50 volt and V0 is equal to 75 volt, right? Now, our task is to find the IS peak. IS peak, switch source current peak value, na? Right? Yes, peak current in amperes drawn from the DC. So that is IS peak. Yes. How to find the IS peak? Whether IS peak and IL peak both will be same or different? Both will be same only. Okay. So how to find IS peak? Which is equal to IL peak, which is equal to IL average plus delta IL by 2, na? So first thing is we need to find IL average and next we can find the delta IL. Okay. So how to find the IL average? So for that we need to find the I0 average, right? So let me write here. You can check, it is a 75 volt, means definitely here voltage is also 75 volt, na? Voltage across 5 ohm resistor, 75 volt, right? So can I write I0? I0 is equal to I0, which is equal to 75 divided by 5, right? So it is equal to 15 ampere, right? Load current is 15 ampere, voltage across load is 75 volt, right? Next, so I0 is 15 ampere. So what is the IL average? Now IL average is equal to 1 upon 1 minus D into I0. So it is 1 upon 1 minus duty cycle 0.6 into, it is a 15, na? Yes. So you can check, it is equal to 15 upon 0.4. 37.5 ampere. This is the IL average. Next, how to find delta IL during T is equal to 0 to T1. During T is equal to 0 to T1. Yes, we can apply KVL to the loop, which is in on state, na? KVL to the loop. VL is equal to VS. VL is equal to VS. What is VL? It is L into di by dt. L into dIL by dt is equal to Vs. Vs is 50 volt. It is equal to 50. So let me write it as. So therefore we can write L is given, or let me write it first, delta IL is equal to 50 into dt divided by L, na? So which is equal to 50 into duty cycle is 0.6 divided by L, 0.6 millihenry. So it is 0.6 into 10 to the power minus 3 into switching frequency 10k. So it is 10 into 10 to the power 3, right? So therefore delta IL, come on, find the value of delta IL. 5 ampere, right? So it is a 5 ampere. Now delta IL is 5 ampere. So what is the IL? IL peak. So IS peak is equal to IL peak is equal to IL average plus delta IL by 2. So it is equal to 40 ampere, right? 40 ampere. Is this clear? Right. So we are almost at the end of the chapter, right? DC to DC converters. Tomorrow, within starting half an hour, we'll finish it. And after that, we'll be starting the DC to AC converter. That is the inverters, right? So as long as this chapter is considered, only the theory bit is remaining. That is the types of the choppers, depending on the quadrant of operation. That is a type A, type B, type C, type D, and type E chopper, right? Only 5 we are having. And these are actually classified according to their quadrant of operation. First quadrant, second quadrant, right? First and second, first and fourth, and all the 4 quadrants, etc. Like this, right? So we're going to discuss those points tomorrow. Hardly theoretical bit is there. And some numericals are there related to our voltage commutation circuit. That also we're going to discuss tomorrow, right? And after that we'll be starting that new chapter, DC to AC converter, right? Okay. Comparatively, DC to DC converter, this chapter is easy, right? Compared to that of your, if you check the rectifier, right? And this DC to DC converter, comparatively very easy questions, possibly they can ask, okay? And you can check the previous exam questions also, ESE as well as the CSE, or you can check for the PSUs or the GATE, right? Okay. So now, if you are having any questions, please ask.
Good evening, sir.
Yes, please.
Sir, I have missed some part of yesterday's class and fulfill the PDF notes. I have understood all derivations, but some little bit doubt in waveforms, sir. Output waveforms.
Okay. 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 In the yesterday session.
Sir, and today buck boost converter also.
Okay.
IC
Okay. Yes,
waveform.
please ask. Please ask.
IC waveform, sir.
IC waveform, na? Just a minute. Let me allow all this also. Yes. Buck boost converter IC waveform, or yesterday's you are saying first?
Yes, sir. Buck boost IC waveform, sir. First.
Buck boost IC waveform. Yes. Yes, here it is.
Sir, the negative half cycle of the IC will be square wave, now, sir. Explain once, sir. I did not get a wave
Okay. Okay.
clarity.
You can check during 0 to T on, during T is equal to 0 to T on. We have drawn the circuit, that is switch is in on state na.
Yes, sir.
So current is flowing like this, inductor is storing the energy. Yes or no?
Yes, sir.
Next, here inductor is storing the energy. This diode will be in off state.
Yes, sir.
This capacitor will be discharging like this.
Yes, sir.
If we apply KCL at node X, if current here is 0, means definitely current here is 0 na.
Yes, sir.
Now this current is 0 ampere. If I apply KCL at node X, it is like a 0 is equal to IC plus I0 na.
Yes, sir.
So IC is equal to minus I0.
Yes, sir.
And I0 is our constant current na, load current constant.
Achha, average current.
Not average. Actually, our assumption is load voltage and load current both are constant, because it is a DC to DC converter. We are interested in giving the constant output voltage na, and output voltage constant means your output current is also constant.
Yes, sir.
Right, so that's why your I0 is constant. So that's why here in the IC waveform, if you check, we are getting that negative pulse, right?
Yes, sir. And half of the output current waveform.
Yes, yes.
Yes, sir. Understood, sir.
Okay. Next.
Hello, sir.
Yes.
Hello,
please.
sir. Hello.
Good evening, sir.
Good evening.
Sir, in workbook, yes, there are some question. I have the 3 diode and 1 thyristor. Is that, sir? Could you explain that one?
3 diode and
1 thyristor in the full bridge rectifier.
full bridge rectifier. In the workbook we have?
Not in workbook. Bits and bytes, volume 2.
In your okay. Practice question.
Yes, sir.
Okay. Yes.
I got
So
but some derivation,
okay.
but
3
it's not
diode
fully
and
clear.
that 1 thyristor like this, na? Yes,
sir.
Just tell me that circuit. I will draw here. Okay. Yes. How it is for single phase?
Yes, sir. RLE.
Actually, this is like this. It is simple circuit. 3 diodes and 1 thyristor.
Yes, sir.
Okay. Where thyristor? Here, suppose. Okay.
Okay, sir.
Load they have given
RLE, sir.
REL. Okay. So this type of circuit we are having, right?
Yes, sir.
This is like, suppose diode is D1. Suppose this thyristor is T1, diode D2 and diode D3. Okay. RLE load, constant current
Yes, sir.
I0 and this voltage is V0. Okay. So simple. Here, how is the V0 waveform? If you check 0 to pi, pi to 2 pi. Okay.
Yes, sir.
Now, out of the positive half cycle and the negative half cycle of the supply, which cycle will be the controlled here? Positive or negative?
Negative, sir.
How?
Sir, because
you
of
check
the thyristor, there no, sir, in negative cycle.
But the thyristor will be there in a forward bias mode during the positive half cycle of the supply or negative half cycle?
Negative cycle, no, sir.
No, you can
Oh,
check.
no, positive. Yes, yes, sir. Positive,
Plus
sir.
minus, here it is plus, here it is minus. No?
Hi.
Thyristor will be in a
Yes, yes,
forward
sir.
bias mode during the positive half cycle of the supply. So
Yes, sir.
unless and until I apply the gate pulse to thyristor T1, yes, our
Yes, sir.
diode will not turn on, or the closed path will not be formed. Okay.
Ah, yes, yes,
Yes
sir.
or no? So what will happen at alpha? Actually, after alpha, the conduction will start. Yes or no? Right? So if the conduction
sir.
is starting like this, okay. So it is like current will be flowing after alpha till pi into this loop, that is V1, D1, T1 conducts, and output voltage will be same as of the supply voltage. So this is a Vs, right? It is like your inductor is storing the energy. Okay.
Hi.
After
Yes,
that,
sir.
what will happen? From pi to 2 pi, from pi to 2 pi, supply voltage is negative, na? So minus here, plus here. So here it is minus, here it is plus. Minus here, plus here. Okay. So in the output, we'll be getting the full cycle na again. Because here we're having only 2 diodes. So as soon as the forward voltage will be maintained, these 2 diodes will be in a conduction mode.
Yes, sir.
Okay. So output voltage will be like this. Right?
Sir, is there effect of the inductance?
Yes, yes.
There is an inductor in the no, sir, in load.
Okay, okay. Effect of inductor. Yes, yes, yes. We need to consider that also. And one more thing, we need to check here because the load
He
current
also
they have
there.
given constant. Yes, please.
Ah, yes, sir. Constant, sorry.
Load current they have given constant, na?
Yes, sir.
Okay. Mhm. Okay, okay. Just a minute. So during D1 T1, it is like till your Vs. Let me draw the full waveform so that it will be better. REL E load constant current. So effect of E will not be observed, but your inductor will store the energy definitely. Let me draw the waveform. Omega T 0. Yes. This is our Vs. Pi, 2 pi, and 3 pi. Suppose that omega t is equal to alpha, I am applying the gate pulse to the thyristor. Okay. So, yes. Alpha to pi, pi to 2 pi, 2 pi to 3 pi. Okay. So we'll be getting this type of waveform in the output. It is same as that of the supply voltage. Here, which 2 devices will be in a conduction mode? It is like D1 T1. Okay. D1 T1 conducts, right? So after that, what will happen? Okay. So either till your, let me write here, VL is equal to Vs minus VR minus E, right? So till VL or till VS is greater than VR plus VE, that is E. Your VS is greater than VR plus E. So VL will be positive. Inductor stores energy. And for Vs less than VR plus E. So VL is negative. Inductor releases energy. Yes. Suppose I am having T like this. I0 is a constant control. Okay. So strictly speaking here, after pi, actually this inductor is supposed to release the energy, right? Or after theta actually.
Yes, sir.
Right? So how the inductor will release the energy? Before theta, definitely it will release the energy through T1, Vs and D1. Okay. And after that, the inductor is having the path to release the energy through T1, D2 also.
Yes, sir.
Right?
D2, 3 also there, sir.
Yes. Yeah, through D3, D2 also, D3, D1 also. So it will be like a 0 here for some time interval. Right? And after that, it again starts D2, D3 will start conducting. So we'll be getting, suppose some type, this type of waveform will be getting. But again, it depends on your value of inductor and your EMF E. If you are saying the load current is a constant.
Hi, sir. I solved some this one, sir.
Huh?
I solved by this way, but I am getting the equation as Vm by 2.2.
1 plus cos alpha.
No, sir. 3 plus cos
Vm
alpha.
by pi.
Vm by 2.2, 3 plus cos
Yes,
alpha I
sir.
got, sir. Vm by 2 pi.
Into
3 cos alpha plus 1.
3 cos alpha plus 1.
Yes, sir. I got that.
Then for that, I think the waveform should be like this.
No, sir. No, sir. Its waveform is
For
correct,
this
sir.
waveform, for this waveform, you cannot get whatever you are saying. For this waveform, it is like pi plus alpha, na? But we
Yes,
don't
sir.
have the pi plus alpha like term here.
Sir, this will start from pi only, sir.
This will start from pi. Then
Because sir, D1, D2 and D3 will be forward biased in the pi to 2 pi. It will be like under D1 will be reverse bias and T1 also reverse bias.
whatever you are saying, na, that is Vm by pi into 3 cos alpha plus 1 something, na?
Yes, sir.
Or it is 3 plus cos alpha something, I don't know. Okay, so in that case, yes, actually the thing is what is happening here, you can check. At alpha I am applying the gate pulse to thyristor. At alpha I am applying the gate pulse to thyristor T1. So T1 D1 starts conduction from alpha till pi. Okay,
Yes, sir.
so output voltage will be like this, na?
Yes, sir.
Next,
First
what will
one.
happen? Hello,
Yes, sir. I'm listening, sir.
is this okay, na?
Okay, sir.
After pi, what is happening? Supply voltage will reverse the polarity. So minus here, plus here. So
Yes,
our
sir.
inductor will release the energy through D3, Vs, D1, D2, and again back to the load in this loop. Because you can check when inductor releases the energy, right? Here Vs energy, Vs is also trying to circulate current in the downward direction. Inductor also is trying to circulate current in this branch in the downward direction only. So Vs and your inductor energy both will be adding only, na?
Yes, sir.
So you'll be getting this type of waveform. For this type of waveform, whatever you are saying is correct. One will be the controlled one, second one will be the uncontrolled one. For this waveform, how to derive the expression? Yes, let me
Yes, sir, I got,
tell
sir.
you. You got na?
I got, sir. I solved this.
Okay, okay. Then your problem was how the circuit operation. That thing only you asked, na?
No, sir. In first,
Yes, why the
second
inductor
cycle.
is not releasing the energy through D3, D1?
Yes,
That you
sir,
are
sir.
saying, na?
Yes, sir. I got, sir.
No,
that, sir.
but thing is here inductor is releasing the energy through D3 Vs because Vs is also in the same direction circulating the current, right?
Yes, sir.
So that's why the thing is from alpha to pi here, D1 T1 will conduct, and from pi to 2 pi, it is like D2 D3 will conduct, right?
Yes, sir.
Yes. Okay. Okay. Okay.
I got,
Sir,
sir.
for this
But please
waveform
be
after
careful.
2
But
pi,
yes.
excuse me, sir.
Huh.
Sir, after 2 pi, it will get some small beta value, sir.
Alpha 2.
Because after 2 pi, we want to again use to triggering pulse to T1, na, sir.
To thyristor T1, the triggering pulse is not given.
Yes, sir. After
Means
2
again, you
pi,
are saying after 2 pi, that is like after 0, you are saying, na?
yes,
So
sir.
supply voltage will be like this, plus here, minus here. But we have not applied the gate pulse to thyristor T1.
Yes, sir.
So what will
Inductor.
happen? So what will happen? Inductor can release the energy through D3, D1 also, na?
Yes, sir.
So that's why it is 0.
Yes, sir. Yes, sir.
Yes. So your negative voltage will not appear. And for this, how to write the V0 average? So please, it is one V0 average is equal to 1 by 2 pi. We need to write integration from, you can check where the two intervals, alpha to pi. During alpha to pi, V0 is same as of the supply voltage. So it is a Vm into sine of omega t, d omega t, plus integration from pi to 2 pi. Actually, Vs is negative, but V0 is positive, na? So we need to write it as a minus Vm
Sine of
into
omega.
sine of omega t. Then and only then you will get the correct answer. Right?
Yes, sir.
Yeah, you can simplify it, you will be getting the answer. Okay.
Sir, one more, sir.
Yes, please.
Sir, just one clarification.
Yeah,
Sir,
yeah.
in the in S, what we are saying in the AC to DC, we are using the SCR, no, sir. In that, why you are not using BJT, and we can say that there is a frequencies are less, not that much of the in kV. That's why not using the BJT and IGBT.
Where frequency of the BJT and IGBT are not means less.
The
you are
switch,
saying?
no, sir. The switching frequency of the IGBT
No,
and
the thing
BJT are.
is, please listen. In the DC to AC to DC circuit, that is a rectifier, we are preferring the SCR. Why? Because the first advantage is SCR requires a very small pulse to turn on.
Yes, sir.
We need not to circulate the gate current for all the time. We need to circulate the gate current for a very short time interval. That is the one advantage. Second thing is SCR is having a drawback that it requires the forced commutation. But in the DC, AC to DC circuitry, we are having the input is AC. So therefore our SCR can turn off by using the natural commutation. Yes or no?
Yes, sir.
So this is the advantage of the SCR. Suppose if I replace the SCR with the BJT, what will happen? If I want to turn on the BJT, like suppose alpha to pi, suppose I want to turn on the BJT, then I need to circulate the that base current, okay, into the base emitter circuit of the BJT for a long time interval. Because as long as your BJT is considered, your MOSFET is considered, okay, in that case, we require the controlling signal to be maintained throughout the operation of the switch, right?
Yes, sir. Yes, sir.
So that's why generally SCR is preferred.
Okay, sir.
But
Thank
here
you so
in
much, sir.
DC to DC converter, we are not using the SCRs. Why? Because in SCR,
Natural
if
combination
input is
also.
DC, it requires the forced combination, right?
Yes, sir.
So that's why SCR is not preferred. Right. Okay. Yes, next.
Hello, sir.
Hello, sir.
Huh.
Sir, I didn't get this, sir. Capacitor current wave current direction in buck and booster.
buck boost capacitor current direction.
Means in the buck case, the capacitor in the off state, the capacitor current will flow, na sir, through a resistance.
Just a minute, let me open it. In the buck boost you are saying?
Sir, means in the buck booster also, in the buck and booster also separately.
What is your doubt? Capacitor?
When switch is off state, sir, the capacitor current is flowing in opposite direction through resistance, no, sir.
Through the load, yes.
So that's why the waveform is constant current, sir. Means the negative part is we have
Yes.
square wave.
Yes. The thing is, when switch is in an off state, it is like
Okay.
capacitor will discharge.
Yes, sir.
So when capacitor discharges, definitely the current should come out from the positive plate, na?
Yes, sir.
So IC should be in this direction. In this branch, it is a downward direction, but in this loop, it is anti-clockwise.
Okay, sir.
And
sir, in
when,
the
sorry, this is when switch is in on state. I'm sorry. When switch is in
Okay.
on state, then it will discharge. When switch is in off state, this inductor will charge the capacitor, na?
yes, sir.
Are you getting the point? We are having
Yes,
the two loops in the active state. When switch is in on state, when switch is in on state, this loop is active, this loop is also active. In this
Yes,
loop, the inductor is storing the energy. In this loop, capacitor is discharging.
Yes,
When
sir.
switch is in an off state, right? That is, it is an open circuit. This inductor will release the energy. Capacitor will be getting charged. Are you getting the point?
Yes, sir.
Right? Okay. And some part of the inductor current will be flowing through the load also. Right?
And sir, the similar is happening in the buck and boost, sir.
Yeah. Same is happening in the buck and boost. That you can analyze by
Means sir,
checking
I
the
didn't get
IC
the
waveform.
IC wave that the current waveform is means passing from negative to up by T on by 2.
That is for buck converter, you are saying, right?
Yes, sir.
For boost, it is same. Whatever we have discussed here, the same is there for boost, na?
Yes, sir.
You can check the boost converter IC waveform and buck boost converter IC waveform. This is same waveform we are having
Yes,
in
sir.
buck
Same
boost
waveform.
and the boost. Yes, but buck we are having the different. So what
Yes,
is
sir,
happening in the buck converter? In the buck
yes, sir.
converter, the thing is, just a minute. Let me tell you. Yes, step down is here. Okay. Is ideal. No discuss that.
Sir,
Yes, please.
sir, can I sit out?
Okay. I'm not getting where the waveforms are. Okay. But the thing is, yes, I got to your point, whatever you are.
Yes, sir. Sir,
You
just
want to
test.
say?
Yes, sir. Yeah, that is the waveform. I mean, that is the
Actually,
question.
the thing is, you can check. It is not like that during 0 to T on the capacitor is charging or discharging. Okay. You can check from T is equal to 0 to T on by 2.
Yes, sir.
We had a IC negative, right? For buck converter.
Sir, it is flowing from negative side to.
Yeah. That is IC is negative, na 0 to T on by 2. IC is negative. T on by 2,
Yes,
I am
sir.
saying.
Yes,
So
sir.
IC
Yes.
negative means it is like capacitor discharging.
Okay.
And from T on by 2 to next, whatever the IC were having the positive, na, till that instant, the capacitor is storing charging actually.
Okay. Means sir, I didn't get that half wave it is charging also and discharging also.
Yes. Because in a steady state, in a buck converter, we are getting this type of operation only.
Okay.
But whereas you can check buck boost and the buck boost, respective to corresponding to your on time, it is like capacitor discharging, and corresponding to the off time, capacity charging. This is there in a boost and a buck boost. But in a buck converter, we are having in between it is crossing to 0.
Yes, sir.
Right? Okay.
And sir, what is the difference between the chopper and this buck boost converter?
chopper and your these converters, the difference
Yeah,
in a chopper means it is a basic circuitry. We
Okay.
discussed the step down, step up chopper, where we observed that the load current waveform, load voltage waveform, it was having a zero value na, for particular interval.
Yes, sir.
So that is the actually disadvantage. We cannot give that kind of supply to any load na. So
Yes,
in
sir.
order to improve that,
Some-
we have connected the inductor and capacitor.
Okay, so means main difference is inductor and capacitor, constant current.
Yes, yes,
voltage.
yes.
Okay,
Hello.
okay, sir.
Sir,
Huh.
sir, I have a
Yes,
doubt that for any circuit condition, I got continuous conduction and inductor current is minimum current is I1 and I2, minimum and maximum current.
Yes.
Then I take that same circuit condition, but changes the R value such that I found some discontinuous conduction.
R value means your load resistor.
Load register, so that discontinuous conduction. Is there any chance of any logic that we can say that I2 is greater than Imax? That previous I2 is
Yes.
greater than that the present Imax, because I changed the circuit condition to by changing the load.
Yes. It is possible. You can check na, because the inductor charging and discharging, it again depends on the value of EL also.
Okay,
Yeah,
but
it depends on you. Suppose for a suppose simple example, suppose we are having a that buck converter, for example. Okay, I am increasing this. I am increasing the switching frequency. Sorry, I am decreasing the switching frequency. So my time T will
Yes.
decrease. Increase.
Yes,
Frequency decreasing means time T will increase. Time T
increase.
increases. Suppose I am increasing the on time also. So whether my maximum current IL max will be constant or it will be increasing.
That is Imax will be
Increasing.
that for a buck converter, it will be
No,
means
simple thing
more
na, you
time.
can check during 0 to T on your switch is closed, the inductor is storing the energy na.
Yes.
So if I am changing the switching frequency, that is nothing but I am changing the time T. Ultimately, it will change my inductor current waveform na.
Yes. But for discharging more time, it will get.
Yeah, it depends. For discharging means when inductor, that is when off state now, when inductor releases the energy. Again, it depends for how much time you are keeping the switch off,
Okay.
right?
Yes,
So
yes.
means whatever we have discussed, it is like for steady state operation, and these are the generalized values we consider na, L, C, like this. If you change
But I
the
can
values
say
of your component, yes.
But I must say that I2 is greater than Imax if I changes to critical value. R2 are critical.
If I2 is greater than Imax, yes, then
I2 will be greater than that is Imax. That Imax is for a critical maximum inductor current. Means for that R critical, that current is Imax.
okay.
In every time, can I say this is true?
No, only means you cannot relate that your R critical and only IL max. You need to
Okay.
relate, you need to consider your L also na. Your frequency also, switching frequency also. If you are keeping, if you are keeping the L is same, switching frequency also same, and only thing is if you are changing the R, then whatever you are saying, okay, that will be true.
Okay.
Right?
Yes,
Right?
yes.
Okay, okay.
And sir, another type is, sir, we got that from AC to DC converter. We get that some input side is having some reactive power.
Yes.
Okay. But in the output, when yes, there is a inductor element is reactive element is present, but when in the output we are getting the power is P, that is real power only.
No, we cannot directly say it is only real power.
Then that
We are
where
finding only real power. We are not finding the reactive power.
in the output side.
Yes. Because your output is not flat at DC, na?
Okay.
It is pulsating we are having. Always keep it in mind in any circuit, right? Your power balance satisfies.
Means,
It is not
okay.
like that only your supply side is having the reactive power and your load is not having any reactive power. No, it will not happen, right? Because we are having a
But-
pulsating type of that thing. Okay.
But if current is constant, that also we are getting some reactive power.
Yes.
Reactive power. Then the output side, if inductor voltage we have to plot, means that storing, discharging, charging, discharging, VL.
Energy storing and energy, yes, releasing.
Then average will be 0. That is VL into I naught is average will be 0 because VL average is 0.
Okay.
But when we calculate for reactive power in the output side for inductor, can we get that found from the input side?
You can check for finding the reactive power whether we need to consider the average value of the inductor. Whether we need to consider the average value of the inductor or RMS value.
RMS.
Then where you are saying that average value is 0.
Means real power is 0. Okay.
RMS value is non-zero.
RMS value is non-zero. Yes.
Right. So that's why it will show some reactive power at the output side also.
Okay.
Right.
Yes.
Because in DC we don't have a concept like a reactive power. But in AC we have, and in AC we are having that power is equal to RMS voltage, RMS current, na?
Because sir, in 2018 one gate question is there.
Okay.
This plot of AC to DC, that output side is constant. That is for DC to AC means inverter mode.
Okay.
Means same type of operation, na? AC to DC, or that is from the DC to AC.
Okay.
He draw a waveform of that capacitor voltage. Capacitor voltage is having some voltage VC1. That VC1 is in the phasor form actually. Means that he plot a
VC1 is
phasor form. Phasor form. That means from where there it is actually the question was question is easy because he drawn the phasor diagram. Otherwise it is difficult to calculate.
Okay.
I will forward that question, sir, actually. From
No,
there,
again, one more thing. In your DC to AC converter, output is AC.
Yes.
Input, even though it is a DC, na? But your source current,
Yes.
right? Whatever the source current we are having at DC side, okay? It is also having some kind of harmonics.
Yes, sir. Harmonics.
Right? So that's why again that will come, means whatever you are saying.
Means he draws for the fundamental one.
Yes.
Okay, sir. Thank you, sir.
Right. Okay. Yes, next. Yes, Anil Kumar.
Hello, sir.
Yes, Avinash, please.
Sir, will you please tell me about C critical, sir? How means we calculate, sir, it?
C critical, how we have calculated? Okay,
Yes.
okay. Yes. Did you get that L critical?
Yes, sir. L critical.
In the L critical, what is happening? The inductor current is changing from 0 to maximum and again reaches to the 0.
0. Yes, sir.
From that same instant, again the next inductor pulse will start, right? Next cycle will start. In the
Yes.
C critical, what will happen if I select the value of capacitor such that voltage across capacitor also changes from minimum value, that is the 0 volt, to the maximum value,
Okay, okay, sir.
and again reaches to the 0 volt.
Okay, okay, sir.
So that kind of concept is there for C critical,
Okay, sir.
right?
Sir, the formula of C critical, how it will be derived?
This in the same way, in the L critical, we are having IL average is equal to delta IL by 2, na?
Yes, sir. Yes, sir.
In the C critical, we had a V0 average, that is VC average,
VC average.
is
Okay.
equal to delta VC by 2,
Okay, okay, sir.
right? VC average means your V0 average, na? Because capacitor is connected in parallel with the load,
Okay, okay, sir.
right? Okay.
Sir, VC waveform in buck boost converter, sir. Will you please explain it, sir?
Yes. Buck boost convert, actually IC and VC waveforms I am not getting. Just now one more student asked the question.
Yes.
Directly I am getting those numericals only. I don't know. This is step up chopper, okay. And here a buck converter directly I am getting.
Yes, sir.
But
Sir,
I think before this we discussed that concept, right?
sir, buck boost converter, sir, actually.
You are saying buck boost?
Yes, sir. Yes, sir.
Okay. Just a minute. Yes. Which waveform you want?
Sir, IC and VC waveform, actually.
IC and VC. Okay. Yes, buck boost converter. Yes. Here it is IC waveform.
Yes, sir. Yes, sir.
0 to T on, switch was on state, na? And we have
yes,
written IC is equal to minus I0.
yes, sir.
You can check. IC we have written it is a minus I0.
Yes, I0. Yes, sir.
So accordingly, I have drawn the IC waveform. It is a minus I0, right?
Yes, sir.
And T on to T, it is IL minus I0.
Yes, sir.
But here your IL average and I0 average both are not same.
Yes, sir.
I0 is lesser than that of your IL average.
Okay, okay,
So
sir.
if I take the difference between this waveform, that is this plot I2 to I1 IL plot, and this I0 will be getting this type of waveform,
Yes, sir.
right?
Sir, this IL minus I0 is applicable for only T on to T period of time, sir.
Only T on to T.
Okay, okay, sir.
That is when switch is in an off state,
Yes, sir. Yes, sir.
right?
Sir, means before T on, our IC waveform will be
Minus I0.
minus I0. Okay.
Right. Okay. So either you can find a delta Q means area over this, or you can find the area of this one.
Okay, okay, sir. Both of the area.
Both areas will be same, right?
Okay, sir. And sir, when we check the continuous conduction and discontinuous conduction,
When we
check sir,
while solving the numerical, okay, keep it in mind. If they give supply voltage, load voltage, and duty cycle,
yes, sir.
we need to check whether it is a continuous or discontinuous conduction.
Okay, okay, sir.
But if they give only supply voltage and load voltage, and if they don't give the duty cycle, then
Yes.
blindly consider it as a continuous conduction.
Sir, if our supply load voltage is given and the load voltage we have found from duty cycle, sir, there is if they are similar, sir, then what we have to consider actually?
Similar means,
Sir, the given V output value and the calculated V output value, if remains same, then
then we need to consider continuous conduction.
continuous conduction.
Yes, continuous. If they
And
are
if-
different, then it is a discontinuous.
Sir, okay, sir. Sir, which value should be greater and less in that means, or any difference we can consider?
No. Actually, we discussed now V0 discontinuous conduction should be greater than V0 continuous,
Okay, okay, sir.
right? And while solving the numerical, we discussed for the numericals where they have given supply voltage, load voltage, and duty cycle. For
Yes.
that specifically, we calculated the V0,
Yes, sir.
right? By considering that duty cycle and the supply voltage. And we observed that whatever the V0 we calculated means that was for continuous conduction. That was less than whatever they have mentioned in the numerical. So that's why we
Yes, sir.
consider it as a discontinuous conduction, right?
Okay, okay, sir. Sir, means calculated value will be greater than the given value in the numerical.
Calculated value should be less than.
Less than. Okay, okay, sir. And
Because
sir,
in the numerical, they will give you the discontinuous, right? Again, it depends. if they give you VS, V0 and D, and suppose they said that the buck converter we are having, and let us consider the VS is 10 volt,
Yes.
and the duty cycle suppose it is given as 0.6, and
Yes.
if they have given V0 is 6 volt, then it
Yes.
is like continuous only, na? D into VS, it is 0.6 into 10, right?
Yes, sir.
Yes, yes. But
Sir,
most
means
of the
our
time, they have
our
asked
cal-
this type of question. Yes.
Sir, our calculated value will be greater than the given value, then it will be continuous, sir. Then
Calculated value will be greater than,
the given value of P output, then we can consider, sir, it is a continuous conduction.
no. Calculated value will not be greater than your given value. They will not ask that type of question. You can check whatever you are saying. You
Yes,
are
sir, yes.
calculating the value of V0 by considering the duty cycle and the supply voltage.
Yes, sir. Yes.
And in the numerical, they have given the V0 average lesser. That
Yes,
you
sir.
are saying, na?
Yes, sir. That condition.
No, they will not.
If happens,
This
sir.
type of condition is not there, na, at all.
Okay, okay, sir.
The calculated means you are considering the continuous conduction and you are calculating. Means it is like the continuous conduction V0 you are calculating, na?
Yes, sir.
And you are saying that in the numerical they have given the V0 average which is less than calculated. But
Yeah.
whether our V0 discontinuous conduction mode is less than the your V0 continuous, no, na? V0 discontinuous is always greater than that of your V0 continuous conduction.
Right. Sir.
Right? So that less will not be there, right?
Okay, okay, sir. And sir, a delta V0 formula, will you please tell, sir, how it comes?
Delta V0.
Yes, sir, yes.
And that is delta Q by C. We know C is equal to Q by V.
Yes, sir, yes. Keep it.
Yes, and from that V is equal to Q by C. So delta V, if we want, we need to find the delta Q.
Yes, sir.
And
Sir,
delta Q means this, like this we calculate. That is a delta Q means what? That is the change in the charge stored. Okay. Or it is like a discharge. So current into time is nothing but your charge, na?
yes, sir. Current into time.
Current is this y-axis and this is time t. Area means what? It is a current into time. So that's
Yes,
why it will
yes.
give the delta Q, right?
Okay, sir. Sir, this charge can be taken from T on to T also, sir. If
Yeah. You can take it from T on to T also. You will be getting the same answer. But why we're preferring to this? Because it is a straightforward, na, rectangular area.
Yes, sir. Yes, sir. Got it.
But here, if you want to find, we need to find the area of this triangle, area of this pulse also,
Yes, sir.
right? So it will take a time. So that's why we're taking this thing, right?
Yes, sir.
Okay. Yes.
Thank you, sir.
Yes. Yes, anyone?
Hello, sir.
Yes, please.
Sir, in this buck boost converter itself, this I0 and IL average, like which is greater and which is lower, sir?
IL and I0.
Which is like more than which one, sir?
Okay. I0 average is less than IL average. Because we have written, na? We have written here, you can check this expression. IL average is 1/1 minus D into I0.
Sir.
Means your IL average is greater, very greater than that of your I0 average comparatively.
Sir.
Right? You can check duty cycle, you can consider any value and you can check. Definitely this 1/1 minus D, definitely this 1/1 minus D will be greater than the 1, na?
Sir.
So that's why your IL average will be greater than the I0 average.
Okay, sir.
Right?
Okay, thank you, sir.
Okay.
Sir, good evening, sir.
Good evening. Yes.
Sir, in 234, sir.
234.
Yes, sir, 234.
Okay.
Sir, while explaining this diagram, it is differing from other converters, sir. Like current flowing, can you please explain again?
Okay. Yes. So here, what is happening? When switch is in an on state,
Yes, sir.
it is like inductor is storing the energy.
Yes, sir. Inductor will
This
store
diode is like feeling the reverse voltage and it will be in off state.
off state, yes, sir.
Right. So one thing is switch is in on state, inductor is storing the energy. One current is in this loop flowing.
Yes, sir.
Second current is capacitor is discharging in this loop.
Yes, sir.
Because at the end, what we require constant output voltage, na?
Yes, sir.
So that's why the construction is like this. When here inductor stores energy, here capacitor discharges.
Yes, sir. Okay, sir.
Next, when switch is in an off state, this inductor will try to maintain the same current, that is to oppose the change in the current. This inductor will release the energy like this.
Oh, okay, sir.
So when inductor releases the energy, capacitor will be charging.
Okay, sir.
Right. So and some part of the inductor current will be flowing through the load also. Right.
Sir, we are not taking intentionally that IC and I not towards.
We are not.
Sir, we are not taking intentionally IC and I not towards upward. Based on
Intentionally,
the
no. Intentionally, we are not taking it. It is by circuit operation only. We are getting upward.
Okay.
Right.
Yes, sir. Okay.
Okay. Yes.
Hello, sir.
Yes, please.
Sir, in this buck boost converter, sir, when it operates as a buck converter and when it will operate as a boost converter?
If your D is less than 0.5.
Okay, sir. D
You
means
can check. We are having the expression D upon 1 minus D, na?
Yes, sir. Yes, sir.
Into Vs, we are having V0 means. So you can check, put any value of D which is less than 0.5 and check. You will be getting V0 is less than Vs.
Okay, sir.
And check when if D is greater than 0.5, then what will happen, right?
Yes, sir. Sir, from the circuit diagram, will you please explain, sir, how it will happen actually?
From the circuit diagram means how it will be buck and how it will be boost.
Yes, sir. Yes, sir.
No, here actually the thing is what we are doing. If you check D is less than 0.5 means your on time is also less.
Yes, sir. On time. Yes.
If your on time is less, then the inductor is getting the lesser time to store the energy.
Yes, sir.
So if inductor is storing the lesser energy, the meaning is overall your output voltage. Okay, because if inductor is storing the lesser energy,
Yes.
then definitely when inductor releases the energy, na?
Yes.
At that time also, when inductor releases energy, your capacitor will be charging.
Yes, sir.
So if inductor has stored a lesser energy, means your capacitor means when inductor releases energy, when
Yes.
capacitor charges, at
Yes.
that time also your capacitor will not be charged to the very high value.
Yes, sir.
Because of this, inductor has stored lesser energy. Okay, so capacitor is not charged to the high value. The meaning is your capacitor voltage means load voltage, na?
Yes.
So you will be getting the output voltage which is lesser.
Yes.
If I increase the duty cycle, what will happen? If I increase the duty cycle increases means your on time T on which is equal to D into T, na?
Yes, sir.
So your on time increases. More the on time means for more time the switch will be in on state.
Yes, sir.
So inductor is getting more time to store the energy.
Yes.
So energy is stored by the inductor is more. So that's why again when it discharges, your capacitor will be charged to the high value, right?
Okay, sir.
Right.
Sir, when this inductor releases energy, sir, then capacitor store
Capacitor charges.
Capacitor charges.
Yes.
And then, sir, this I0 current not flow, sir?
Yeah. Some part of the inductor current is flowing through this load also.
Okay, sir.
Otherwise, your I0 will not be constant, na?
Yes, sir.
Yes. Okay.
V0 and I0 both are constant in means.
Yes.
Okay, sir.
Yes, Navdeep. Yeah, do you want to ask something? Jessica?
Yes, sir.
Yes.
Hello.
Yes, please.
Sir, during this continuous conduction also will load current will constant.
During this continuous conduction?
Will load current will constant or different, sir? Or it will be zero?
Load current is constant.
Even during discontinuous conduction?
During the discontinuous conduction, yes. Actually, during the discontinuous conduction, it depends again to what value of your inductor is there and what value of the capacitor is there.
Sir, if we will take more value of capacitor, then it will continue.
Then it will be continuous only.
Sir, then why we are calling it discontinuous?
Because your inductor current is not continuous, na?
Only because of this.
Yeah. Because of that only. If you check the previous whatever the discontinuous conduction operation we have discussed, or in that derivations also whatever we have derived, there which waveform I have drawn? I have drawn the waveform of IL, na?
Yes, sir.
Right. So due to that IL, it is a continuous and discontinuous variable.
Okay, sir.
Sir.
Yes, please.
Sir, what is the purpose of this diode, sir? We are connected here.
You can check, na. Actually, we are interested in when switch is closed, na. When switch is closed, all the energy, okay, will be, or all the current should be flown through this inductor only, so that inductor can store more energy.
Okay, okay.
Right, this is the one thing. And one more thing is, suppose if this diode is not connected, means indirectly it is a short circuit here. So what will happen when inductor releases, when capacitor discharges, some part will be flowing like this and remaining part will be flowing like this also.
Yes, sir.
So in order to avoid that, actually this diode is connected.
Okay, sir. Sir, instead of diode, we can connect any other element. Means
which element?
Sir, any element, any power electronic device. Other than
No, why you are interested in putting that controlled device there? If you put the control, because diode is a passive device, it is an uncontrolled device. As soon as it becomes polarized, it will perform its function. If you put the control device there, then again I need to apply that gate signal, controlled signal, right?
Yes, sir.
So it will it will increase the complexity of the circuit, right?
Okay, sir. So, sir, it can be replaced by any high value of resistance. Means if our purpose is to not to flow the current from that direction, sir, we can.
High value of resistor can do the job, but the thing is, whether your that high value of resistor will cause the power loss.
Yes, sir.
Right?
Yes, sir. Yes, sir.
Yes.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Right. Okay. So thank you. Thanks to all of you. Okay. Hello. Do you want to say something?
No, sir.
Okay. Right. Okay.
Thank you, sir.
Right. Okay. Thank you. Thanks to all of you.